fixed route ranges and perhaps installed a more reliable public transport system. Unfortunately, astronomy is rarely that considerate.
Country from a war. Century foot before sleep.
Rocky, or even remotely suitable for a quiet afternoon outdoors. It may be a scorched ball of lava, a dense world under crushing gravity, a planet covered by a deep global ocean, or a small gas-rich planet with no solid surface that anyone can sensibly stand on. The name mainly tells us that the planet sits in a broad size or mass range above Earth and below the ice giants Uranus and Neptune. It is a practical label, not a promise. NASA describes super-Earth planets more massive than Earth, but lighter than Neptune and Uranus, with possible compositions that include rock, gas, water, or mixture of all three. They belong to a family of worlds that has no clear equivalent among the 8 planets orbiting our Sun. That is the mystery we're settling into tonight. Why do these medium-sized planets appear so often in the systems we've discovered, while our solar system seems to have skipped the entire category? Before we begin, where are you listening from tonight? Perhaps you're in a large city where only the brightest stars make it through the streetlights. Perhaps you're somewhere quiet enough to see the Milky Way. Maybe you're already in bed, with the room dark and your phone resting on a question angle above your face. And since we're talking about distant worlds, here is another question to consider. If you could visit one planet beyond our solar system, would you choose a world that looked comfortably familiar, or would you rather see something completely strange? There is no need to decide quickly. Interstellar travel is not currently taking bookings, and the luggage allowance would probably be unreasonable. If you find these slow journeys through science soothing, you can like the video and subscribe to the channel. It helps this quiet corner of the internet reach other people who enjoy learning about planets, stars, and the occasional scientific puzzle, while gradually becoming less concerned about staying awake. You can also leave a comment telling us where you are listening from. It is always pleasant to imagine people in different places sharing the same subject at roughly the same moment, even if their clocks disagree about what that moment should be called. Now, make yourself comfortable. Let the day become less important for a while. Consider the small group of planets we know best. Close to the Sun we have Mercury, Venus, Earth, and Mars. They are the rocky planets. Mercury is small, airless, and heavily cratered. Venus is almost the same size as Earth, covered by a thick atmosphere, and hot enough at the surface to make lead melt. Earth has oceans, moving continents, weather, life, and an impressive ability to fill kitchen drawers with cables that belong to devices no one remembers owning. Mars is smaller, colder, marked by volcanoes, canyons, dust, and evidence of a wet
Not everyone. I really hope everyone enjoyed the meteor shower and the total eclipse earlier. Wicked, right?
Uranus and Neptune, often called ice giants because their interiors
now,
contain larger proportions of
it's all over.
substances such as water.
I mean, it's not all over.
Jupiter and Saturn do. The size
It
of the
probably
planets
is.
do not
Yeah,
fall
no, it's all over.
Earth is the largest rocky planet.
You might be able to find
Neptune,
some streams in
smallest
like
of
different
giants, rules 4
countries,
times
but
Earth's diameter,
it's definitely all
more than
over England.
17 times its mass.
So it's
Between
bad
them is a
time.
very noticeable gap. There is no
Right.
planet twice Earth's diameter. There is no planet 5 times Earth's mass. There is no close orbiting chain of worlds packed between Mercury and the Sun. There is no compact group of planets completing their years in a few days or weeks. Our inner system contains 4 relatively small rocky planets, followed by a wide region, followed by giant planets. For a long time, this arrangement did not seem unusual. It was the only planetary system we knew. Textbooks could present it as though nature had followed a sensible plan. Small rocky planets near the star, large gaseous planets farther away, and a collection of leftover material at the edges. It looked organized. It looked almost instructional. Then astronomers began finding planets around other stars. The first discoveries were difficult, surprising, and enormous. Planets are faint and stars are bright. Trying to see a planet beside its star can be like trying to notice a small moth flying beside a lighthouse from many kilometers.
Yes, it's
Early searches therefore found models that produce
Over there.
large sequence, massive planets tugging strongly on their stars,
that
or large planets crossing in front of them,
maybe.
blocking a measurable amount of light. Many of the first known exoplanets were hot Jupiters, giant planets orbiting extremely close to their
Oh, dear.
stars. They were already a warning
Getting
that the
tired.
solar system was not a universal template. A Jupiter-like planet was apparently capable of circling the star in a few days. This meant either that giant planets could form in places where many theories had not expected them, or that planets could move far from the locations where they formed. Then instruments improved. Surveys became larger. Space telescopes watched thousands and later hundreds of thousands of stars. Kepler in particular was designed to detect the tiny dimming caused when a planet passes across the face of its star. These events are called transits. A single transit is not enough to establish much, but repeated dips at regular intervals can reveal a planet's orbital period and approximate size. As the results accumulated, astronomers discovered that many planetary systems were not arranged like ours. They found stars with several planets orbiting closer than Mercury orbits the Sun. They found worlds larger than Earth, smaller than Neptune. They found complex systems in which multiple planets compete in their orbits in less time than what it takes to get through a single season. Super-Earth-sized, slightly popular relatives, often called sub-Neptunes or mini-Neptunes, emerged as two of the most common types of planet found on modern surveys, despite being a type of an obvious representative in our solar system. NASA describes them as among the common planetary classes revealed by exoplanet research, and emphasizes that both are unfamiliar precisely because our own system is quite likely. The word everywhere intimates taking into little care. Astronomers have not inspected every star in the galaxy. We have not discovered every planet, even among the nearest stars. Our detection methods are also strongly biased towards certain kinds of worlds. A planet orbiting close to its star transits more frequently, if its orbit happens to line up with our viewpoint, and it causes its star to wobble more strongly than a similar planet of a distant orbit. Close planets are therefore easier to find and confirm. So super-Earths are not literally everywhere. There may be countless systems without them. Some stars may have only small working planets. Others may have giant planets on wide orbits. Many systems remain beyond the reach of our current instruments. Still, after accounting for the limits of the surveys, astronomers have good reason to think that the difference between the sizes of Earth and Neptune, particularly in relatively short orbits, are genuinely common. One study using extreme technical data estimated that orbital periods shorter than 50 days on small undwarfed stars, there were roughly 0.46 planets per star, with a radius range from 1.5 to 2 times Earth's radius. That's not even exactly small stars, exactly one meteor-watching super-Earth. Planet statistics are as tidy in supermarket shelves, which means that across a large population of stars, planets in that range occur frequently with a major feature of the galaxy planetary inventory. This makes the solar system seem even more interesting. Imagine a tall neighborhood where every house has a bicycle in front of it. Some have one, some have three, some have something that may once have been a bicycle, but now appears to be supporting a flying car. Then you reach your own house and realize there is never been a bicycle there at all. The absence does not prove that anything went wrong. Perhaps your house was built differently. Perhaps someone removed it long ago. Perhaps the local conditions never allowed one to appear. Once the fact becomes obvious, the empty space starts asking for an explanation. That is roughly where planetary science finds itself. Our solar system may form through sequence of events that prevented super-Earths from growing. It may have fallen and then lost. Material that could have been larger than a planet may have been blocked, scattered, swallowed by the sun, or incorporated into other worlds. Jupiter may have played an important role in forming a changing the movement of gas bubbles and young planetary bodies. Saturn may have altered Jupiter's movement. The young solar system may have passed through periods of migration and instability that prevent configuration. Unlike most of the planet systems known by the hangout stars, there is no single firm answer. Several models reproduce parts of what we observe, each depends on a vector which more than 4.5 billion years ago in a disk of gas and dust that no longer exists. Planet formation is evidence, but does not use security camera footage. Researchers reconstruct the past using planetary masses, orbital shapes, meteorites, asteroid compositions, computer simulations, observations of young stars, and comparison to exoplanet systems. It is a little like arriving in the kitchen one after dinner and trying to determine the recipe by examining the dirty dishes, a few crumbs, the temperature of the oven, and one person's confident but unreliable claim that it was definitely on fire. One influential line of research suggests that close-in super-Earth systems require a great deal of solid material to be liquid. This may happen as small pebbles drift through the planet-forming disk, or as glowing planetary embryos migrate toward the star. Reviews of planet formation models emphasize that radial movement, migration, and later orbital instability are central to explaining both compact super-Earth systems and the very different structure of our solar system. In many young systems, several rogue planets can move inward through the galaxies. Their orbits can become linked in resonant chains, meaning their orbital worlds settle into simple numerical relationships. One planet might orbit 3 times for every 2 orbits of another. These arrangements can remain stable while the gas is present. When the gas disappears, the system may become unstable. Planets can collide, merge, shift into new orbits, or be ejected. The result can be a group of super-Earths or sub-Neptunes close to the star. The system does not want that way. Mercury takes 88 days to orbit the Sun. There is no planet inside its orbit. By exoplanet standards, habitable regions, place in the many known compact systems will fit several planets into the space between the Sun and Mercury's planet. Their planets may not be comfortable places, but they are efficiently built in real estate. This difference raises several possibilities. Perhaps the disk around the young Sun contains less material in its innermost region than many other disks. Jupiter's core formed early enough to interact with the drift of pebbles, cutting off the supply that might otherwise have built one or more super-Earths. Every day, plan is in every moment of Earth has a level. The next review comparing solar system formation with exoplanet systems argues that the early formation of Jupiter's core may have blocked and will drift material and limited the growth of the terrestrial planets. In that picture, Earth remained Earth-sized, partly because Jupiter prevented the other system from receiving a larger delivery of building material. This turns Jupiter into a complicated character. It is tempting to call it a protector because its gravity influences comets and asteroids, sometimes redirecting objects that might otherwise enter the solar system. Jupiter can also send objects inward. It does not stand at the edge of the rocky planet where the security barrier gravitational roll becomes an object in the orbit of the tiny. During the solar system's formation, to know a plan before. Some models propose that it will do more than 1.5 year, reshaping the disk and affecting the amount of material available to bring Mars where Venus and Mercury. Other models focus on the early instability in the giant planets. There are also scenarios in which the solar system must continue larger planets, migrated into the sun, or collided and were destroyed before the planets remain finish forming. These ideas are not interchangeable, and branching treated as a central biography of the solar system, but competing or partnering or attempts to explain the same evidence. The important point for tonight is that planetary systems are related to theory. They grow while the disk is changing. Planets migrate. Material builds. Gravity produces chains, collisions, gaps, and occasional disasters. A small difference early on can lead to a very different system hundreds of millions of years later. That may be why asking, why do we not have a super Earth, is more useful than it first appears. The question is not only about incident to a planet, it is about why Earth has the mass it has. It is about why Mars is so small. It is about why Mercury is alone so close to the Sun. It is about why Jupiter remains far away instead of becoming a hot Jupiter. It is about whether our arrangement is rare and which events are possible. It also matters for the search for life. Super Earth can be larger than our planet without being habitable. Greater mass might have the reputation and hold an atmosphere for a long time. It can also produce high surface gravity and intense internal pressure. A planet close to its star will be heated far beyond the point where liquid water can remain on the surface. The world with a deep hydrogen-rich atmosphere may have temperatures and pressures that bear little resemblance to Earth. Another may be covered in water, with an ocean so deep that high-pressure ice forms at the bottom, separating the liquid water from the rocky material. We are only beginning to learn how varied planets can be. Their masses and radii can sometimes reveal average density, but density alone does not always tell us whether a planet is an iron or a rocky mountain, a thick atmosphere, or several of those at once. Two planets of similar size have very different compositions. This is one reason the term super Earth is misleading. It sounds specific, but it gathers together words that have little in common yet fitting between familiar size limits. A planet can be described as a super Earth in one study and as a sub-Neptune in another, depending on its measured radius, mass, density, atmosphere, and the classification system being used. There is also an observed feature known as the radius value, the relative shortage of planets in the narrow size range between underwater super-Earths and gas-rich sub-Neptunes. One explanation is that some young planets begin with thick atmospheres, then lose much of that gas because of radiation from their stars or heat left from formation. The smaller survivors become exposed rocky worlds, while larger planets retain more of their envelopes. NASA has reported observations of closely linked Neptunes losing atmospheric gas, offering evidence that at least some planets can evolve from heavier worlds towards smaller super-Earth-like states. So, the population we see today may not be the population that first formed. Planets change, atmospheres escape, orbits shift, worlds collide. A neat chart showing planet sizes is actually the final frame in a very long process. Our solar system has experienced its own changes, of course, really likely formed after a major collision involving the Earth. Uranus rotates on its side, probably because of violent events early in its history. Neptune may have migrated outward. The giant planets disturb smaller bodies and help structure the asteroid belt and Kuiper belt. The present arrangement is not a pristine model, but gently into position. It is what remained after a busy youth. It surprises not that our system has a history. Every planetary system does. It surprises that so many other histories appear to produce planets in the size range that ours is. It is possible that a distant super-Earth still belongs to the solar system. The proposed planet Mars exists. We have several times Earth's mass in the orbit far beyond Neptune. NASA notes that such a planet would help fill the gap between Earth and ice giants, although planet 910 Vertical has not been directly detected. Even if a distant planet is eventually found, however, it would not make our system resemble the complex super-Earth systems discovered by Kepler. A remote, cold world taking thousands of years to circle the Sun is very different from several planets orbiting close to their star in days or weeks. Without a missing science, but what common architecture makes the mystery so striking. And now, the known solar system contains no confirmed super-Earth. It gives us 4 rocky planets, 4 giants, and a great deal of smaller material. Around our stars, we often find categories between those groups. The contrast may tell us that the path leading to Earth was not the standard path. That does not automatically make our system unique, and it certainly does not prove that systems with super-Earths cannot support life. It simply reminds us that the first planetary systems humans discovered may not be the best example of what planets usually do. For centuries, people looked at the solar system and tried to understand why it had the structure. Now we can compare it with thousands of other systems. The question has changed. We're no longer asking only how our planets formed. We're asking why they formed differently. Before we can follow the route of the dust covering its young planets, Jupiter, and the rest of the early solar system, we need to settle one deceptively simple matter. When astronomers call a planet a super-Earth, what exactly are they describing? The answer is less tidy than the name suggests. When astronomers call a planet a super-Earth, they're not saying that it is an enlarged copy of our world. They're not promising continents, blue oceans, breathable air, trees, weather, or a convenient place to put a small holiday cottage. The label usually means that the planet is more massive than Earth, but less massive than Uranus or Neptune. When only its radius is known, the same terms often apply to worlds larger than Earth and smaller than Neptune. These are commonly described super-Earths as planets that can reach out 10 times on its mass, while also noting that their compositions will include rock, water, gas, and some mixture of all 3. That definition sounds simple until astronomers begin using it. One research team may define super-Earth measured by mass. Another one uses the telescope that measures size and direction. A survey might place the lower boundary at 1.25 times Earth's radius, while another might begin at 1.5. The upper edge includes so many. Some astronomers stop using the term into Earth altogether. Others allow it to overlap with Neptune and some Neptunes, particularly when the planet's internal composition is unknown. There is no small official desk somewhere in the observatory, but every newly discovered planet is examined, stamped, and placed into a perfectly agreed category. The terminology developed while the discoveries were being made, and the discoveries turned out to be more complicated than the original labels. The word super refers to size or mass, not quality. The words are roughly the same as the word super in supermarket, which does not guarantee that tomatoes will grow. A planet 5 times as massive as Earth may be a dense rocky world in a large world in 4. Maybe a water-rich planet containing enormous quantities of ice and liquid. It may have a rocky center hidden beneath a thick temperature and cooling atmosphere. It may resemble a smaller Neptune more than a larger Earth. Without additional measurements, its mass alone cannot tell us which of these possibilities is correct. Focus presents the same problem. A planet twice Earth's diameter is not simply Earth, but twice as much bigger than Earth. Volume increases much faster than diameter. A world with twice Earth's radius has 8 times Earth's volume. If its mass is only 5 times Earth's mass, then its average density must be lower than Earth's. That lower density may suggest large amounts of water in the atmosphere or above. If the same sized planet has 10 or 15 times Earth's mass, it may contain more rock than matter, produce much stronger surface gravity. Astronomers therefore try to measure both radius and mass. Once they have those values, they can estimate the planet's average density. Density does not provide a complete internal map, but it narrows the options. very low density world probably contains a large amount of gas. A high density world is more likely to contain substantial rocky matter. Several different materials can still produce similar densities, so the result is closer to a useful clue than a full medical scan. This uncertainty is not a weakness in science. It is the reason science continues. The difficulty begins with the fact that planets outside the solar system are extremely hard to see. The star produces an enormous amount of light. The planet beside it reflects or emits very little by comparison. Even a large planet can disappear in the glare of its star, especially when the entire system is many light years away. For most known exoplanets, astronomers did not begin with a photograph. They began with a repeated change in starlight. One of the first successful methods was radial velocity, sometimes called the stellar wobbling method. The planet does not technically orbit the exact centre of its star. The planet and star orbit a shared centre of mass. Because the star is much heavier, its movement is small, but it is not zero. As the star moves slightly toward Earth, its light shifts towards shorter, bluer wavelengths. As it moves away, the light shifts toward longer, redder wavelengths. Astronomers measure this repeating Doppler shift with precise spectral graphs. The pattern can reveal the planet's orbital period and provide an estimate of its minimum mass. And as it describes radial velocity as a way of detecting the motion produced when the orbiting planet gravitationally pulls its star away from Earth. In the early years of exoplanet activity, this method naturally favored large planets orbiting close to their stars. A heavy planet produces a stronger gravitational pull. A short orbit repeats quickly, giving astronomers several cycles to measure. A small planet in a wide orbit produces a weaker signal and may take years to complete a single journey around its star. This was one reason the first exoplanet discoveries made the galaxy look crowded with enormous worlds. In 1995, the discovery of 51 Megaside B showed that a giant planet could orbit a sun-like star in just over 4 days. It belonged to a class that became known as hot Jupiters. Nothing like it exists in the solar system. Jupiter takes nearly 12 years to complete an orbit and remains far from the Sun. The Jupiter-mass planet almost touching a star was not what many astronomers had expected to find. The result was not evidence that most planets were hot Jupiters. It was evidence that hot Jupiters were relatively easy for instruments of the time to detect. The first fish caught from a pond may be the one most likely to bite the hook, not the most common fish in the water. The spectrographs became more precise and astronomers collected longer sets of observations. Smaller signals began to appear. In 2005, researchers reported a low-mass planet orbiting a nearby red dwarf GJ876. The planet, now known as GJ876d, completed an orbit in less than 2 Earth days. The original analysis gave a minimum mass of 5.9 Earth masses and a likely mass of roughly 7.5 Earth masses under the team's preferred orbital model. It was far lighter than the giant exoplanets that had dominated early discoveries. It became one of the important early examples of what astronomers would call a super-Earth. It was not an Earth twin, but orbited extremely close to its star and was likely exposed to intense heat. More importantly, radial velocity did not provide its radius, as the planet did not pass across the face of its star from that point of view. Astronomers could estimate its mass, its physical size and internal composition remain uncertain. That limitation shows why planetary radius can become slippery. The mass of several Earths faces a world in super-Earth territory under that specification. Yet without a radius, it would be difficult to tell if the planet is mostly rocky or surrounded by a significant gaseous envelope. Another detection method is needed to measure size on a large scale. That method is the transit. The transit occurs when a planet passes between a star and a telescope. The planet blocks a small fraction of the star's light, producing a temporary dip in brightness. If the dip repeats at regular intervals, it may indicate an orbiting planet. The size of the dip helps astronomers estimate the size of the planet relative to its star. A large planet blocks more light. A small planet gets less. If astronomers know the star's radius, they can calculate the planet's radius. The method seems wonderfully straightforward. Watch a star, wait for it to become slightly dimmer, and then to planet, retire early. In practice, stars change brightness for many reasons. They have spots, flares, pulsations, and unfiltered activity. Two stars orbit each other and produce an eclipse that resembles a planetary transit, especially when their light is blended with another nearby star. Instruments produce noise, spacecraft move, detectors age, background objects interfere, convincing planet signal must repeat consistently and survive along to chance. The orientation must also be fortunate. Most planetary orbits are not aligned so that the planet passes in front of the star is seen from them. Perfectly real planetary systems remain invisible to the transit methods simply as reviewed from the one angle. Closer planets and planets transit from distant ones, because their orbits cover a larger portion of the sky from the star's perspective. They also transit more often. A planet with a 3-day year produces hundreds of events during a mission. A planet with an Earth-length year produces one transit every 12 months. The telescope must observe at least several of those events before the pattern becomes persuasive. The transit method, therefore, has its own preference for large, close-orbiting planets. It does not give astronomers an unbiased list of everything that exists. It gives them a list shaped by orbital alignment, planetary size, orbital period, stellar brightness, observation time, and sensitivity of the instrument. Even so, transit surveys change the subject completely. The French-led Corot space mission produced one of the major early steps. In 2009, researchers reported Corot 7b, a planet with a radius of about 1.68 times Earth's and an orbital period of only 0.85 days. It was described as the first super-Earth with a measured radius. Its transit blocked only a tiny fraction of the star's light, showing that space telescopes could detect planets much smaller than hot Jupiters that would be easiest to find. Corot 7b was not a violent place. It orbited so close to its star that its surface was expected to be extremely hot. Later efforts to measure its mass were difficult because the host star itself was active, creating signals that could be confused with the gravitational pull of the planet. Published mass estimates varied, which demonstrated another recurring difficulty in super-Earth research. Small planets produce small stellar wobbles, and stars are not always cooperative enough to remain perfectly still while astronomers measure them.
Sorry, but it's impossible to hold and watch. You won't call me up. You don't say, that's your body. I feel like it's locked. It's really fun to go outside to be as consistent as possible. It's easy to solve because of the dream. And then to continue to keep doing, I guess, it's just loud. It's hard. It's attainable. It's easy. I was able to find it. It's able to walk through your experience or to walk through your generation. Feel more on the
The planet is important because it looked like Earth. It's both a small radius and a planetary mass to be studied. Astronomers were beginning to move beyond simply finding planets. We could start asking what those planets might be made of. Then Kepler arrived. NASA launched the Kepler Space Telescope in March 2009. Its main task was to stare continuously at a large field containing roughly 100,000 stars and measure their brightness with extraordinary precision. Kepler was not designed to chase one planet at a time. It was built to conduct a census. For years, the telescope watched the same stars and waited for repeated dips. This approach allowed it to find planets with a wide range of sizes and orbital periods, including systems containing several transiting worlds. By the time the spacecraft was retired in 2018, Kepler had produced more than 2,600 confirmed exoplanet discoveries, and a much larger collection of candidates and signals for continued analysis. Kepler's greatest contribution was not in a single planet, it was the population. Before Kepler, astronomers knew that exoplanets existed, but the available samples were heavily weighted toward large worlds. Kepler watched enough stars with enough precision to reveal that small planets were not rare exceptions hiding among giants. The change became obvious very quickly. In an analysis of the mission's first 4 months of data, published in 2011, the Kepler team reported 1,235 planetary candidates. Using the size categories adopted in that study, 68 were approximately Earth-sized, 288 were classed as super-Earth-sized, and 662 were classed as Neptune-sized. More than 74% of the candidates were smaller than Neptune. The number of candidates rose toward planets 2 to 3 times Earth's radius, and then declined for larger sizes. Those early candidates were not all confirmed planets, and later measurements changed the estimated sizes of some of them. The stars themselves had to be characterized more accurately. False positives had to be removed. Detection biases had to be calculated. Even so, the broad result remained. The space between Earth and Neptune was not empty. It was crowded. This is where the statement that super-Earths are everywhere begins to make sense. Astronomers do not mean that every star has one. They mean that after surveying large numbers of stars and collecting planets, the telescope detected worlds in the Earth to Neptune size ranging very high frequency. Corrections are essential. Suppose Kepler watches 100 stars and detects 10 transiting super-Earths. It would be wrong to conclude immediately that 10% of stars have such planets. Only a small fraction of planetary systems are aligned to produce transits from Earth. Some planets transit, but their signal is too weak for detections of Earth. Some orbit slowly and do not transit enough times during the observing period. Some stars are easier than others. Some candidates are actually eclipsing stars or other false positives. Researchers estimate how often their platforms will detect artificial planet signals inserted into real data. They calculate the probability that a planet will begin orbit in transit. They model the stars that they observed and the candidates that they missed. On this, they attempt to reconstruct the population. The procedure is a little like estimating how many nocturnal animals live in a forest by placing cameras along several paths. Photographs are useful. First, you must know which animals use the paths, which ones avoid the cameras, how often the cameras fail, and whether the suspicious shape in photograph number 47 is an animal or a shrub moving mysteriously. Different surveys and statistical methods produce somewhat different rates. The exact number depends on the type of star, the planet size range, and the allowed orbital periods. The general conclusion, however, is important in particular. Planets a little larger than Earth and smaller than Neptune are common, especially in short period orbits. A study of the full Kepler data set around small and dwarf stars estimated at 0.46 super-Earths per star for planets between 1.5 and 2 Earth radii, orbital periods shorter than 50 days. Across the broad range of 1 to 4 Earth radii and periods shorter than 200 days, the estimate rose to about 2.5 planets per M4. That figure includes Earth-sized planets sub-Neptunes, as well as the narrower super-Earth category. It demonstrates how densely populated this overall size range appears to be. Studies of sun-like stars also found that the radius distribution take large numbers of planets between Earth and Neptune. One analysis of more than 76,000 Kepler target stars estimated an average of roughly 0.46 planets per star between 1 and 4 Earth radii in orbit in 20 to 200 days, with a distribution peaking around 2 to 2.8 Earth radii. Including closer planets increase the estimated occurrence. These results do not mean the galaxy manufactures one standard model of super-Earth, places it around nearly every star. They mean that when planets are sorted by size, there is a large population occupying a region absent from our own solar system. Further analysis revealed that even this population is divided. In 2017, the California Kepler survey used improved measurements of more than 2,000 Kepler planets and found a relative shortage between about 1.5 and 2 Earth radii. Smaller, close-orbited planets tended to gather below roughly 1.5 Earth radii, while another population appeared around 2 to 3 Earth radii. The gap became known as the radius gap, or radius valley. This was a major clue. The smaller group was generally associated with rocky planets. The larger group was more likely to include rocky cores surrounded by layers of lower density gas. A surprisingly modest amount of hydrogen and helium increased the planet's measured radius substantially. The rocky core and somewhat more massive than Earth can therefore appear much larger if it retains a gaseous envelope. The distinction also suggests that super-Earths and sub-Neptunes may be connected by evolution. Some planets may begin with gas envelopes and keep them. Others may lose their gas through intense radiation from their stars or through heat left from their formation. Stripped planets remain smaller rocky cores. Observations of young, close-orbited new Neptunes using atmospheric material support. The idea that at least some planets can move from one observation category to another over time. This makes the name super-Earth even less straightforward. You can describe a planet that formed as a rocky world and stayed rocky. You can also describe the exposed core of the former sub-Neptune. Two planets with the same present radius may have reached that size through different histories. Mass complicates the picture further. A rocky planet can become more massive without increasing the radius as rapidly as a gas-rich planet, because gravity compresses its interior. At high pressures, rock and metal do not remain as loosely arranged as they are near Earth's surface. And the material also increases compression. A planet with several Earth masses may therefore be only modestly larger in diameter. Meanwhile, the low-mass atmosphere is occupying an enormous plane. The gases in the outer layers are not very dense, but they extend far above the solid core. A planet that is mostly rock by mass can still look much larger during a transit because the starlight is blocked by its atmosphere. Astronomers need several kinds of observation to separate these possibilities. Transits provide radius. Radial velocity can provide mass. In systems with several closely matched planets, small changes in transit times can reveal how strongly the planets pull on one another, often another way to estimate mass. Spectroscopy during transit may reveal atmospheric gases when starlight passes through the planet's outer layers. Infrared observations can measure changes in emitted heat as the planet moves around its star. Each method fills in part of the description, and each method has limitations. A super-Earth that does not transit may have a measured minimum mass, but no known radius. A transiting planet or a photoactive star may have a good radius and an uncertain mass. Clouds can hide atmospheric features. Stellar activity can imitate or distort signals. A planet may receive the same amount of energy as Earth while having a completely different atmosphere and surface pressure. The phrase potentially habitable super-Earth is therefore handled correctly. Being in a star's habitable zone only means that the planet is at a distance where liquid surface water might be possible under suitable atmospheric conditions. It does not confirm water, atmosphere, the rocky surface or life. A planet can occupy correct orbit and still be dry, airless, frozen, or covered by an atmosphere thick enough to produce extreme temperatures. Size is not destiny. Even the word rocky inherently secret variety. Mercury is rocky, but has a very large iron core. Venus is rocky, but surface conditions are lethal. Earth is rocky with thunder oceans. Mars is rocky, cold, thin air. All four belong to the same broad physical class, yet no sense will travel over platform in the same way. Super Earths probably show at least as much diversity. Some orbit red dwarfs and complete a year in only a few days. Some travel through habitable zones. Some are heated enough to maintain habitable surfaces. Some may have permanent dolomite sides because their rotations are not synchronized with their orbit. Others may circle sun-like stars at wide distances. The classes united all by our measurements and by a shared environment.
The very fact that some of the stuff of life, even if our hands are not having very so much stuff in the sun, so they have to control the position of other possible direction and to position the direction of every single direction and every single measure. For summer we have to do it. All hard practice is regulation.
Order of all the suns and galaxies that unfold the merciful entertainment with a screen page for get lunch with ET, weekend's best.
School and sexual to a nice but in many cases, it's just 2 days. And it's fine for Christmas. That's what I'm doing. NASA's Transiting Exoplanet Survey Satellite TESS continued the census after Capcom. Launched in 2018, TESS also uses the transit method, but it concentrates heavily on bright, relatively nearby stars spread across most of the sky. Its targets are often better suited to follow-up observations than many of Kepler's more distant stars. TESS identifies candidates when ground-based telescopes and space observatories help determine whether the signals are planets and what those planets may be like. Kepler answered an important statistical question: how common are different kinds of planets? TESS helps provide targets that can be examined in more detail. Other observatories measure masses, define orbits, search for neighboring planets, and study atmospheres. Together, these efforts have changed the meaning of the night sky. The sky appears as one steady point of light and has several planets moving close around it. One may be slightly larger than Earth, mostly rocky. Another may have thick envelope and deep interior unlike anything in the system. For Earth, the system still looks like a single dot. Its complexity is hidden inside tiny changes in brightness and wavelength. That hidden complexity explains why astronomers did not realize immediately that super-Earths were common. The planets were always difficult to see, and the first instruments were better at making giants. Once telescopes became sensitive to smaller worlds, and surveys watched enough stars for long enough, the missing population occurred. The discovery did not produce a neat new category, it produced a problem. The larger question is why nature produces so many planets in this range. The answer cannot come from classification alone. It requires looking at the raw material around lone stars, the speed at which particles grow, the movement of dust and gas through the disk, and the moment when a grown planet becomes large enough to hold an atmosphere. Those processes repeatedly create worlds larger than Earth and smaller than Neptune. Once astronomers began counting them properly, the scale of the difference became difficult to ignore. Our solar system contains 4 planets smaller than Earth or only slightly larger, followed by a 7th jump to Neptune, which has almost 4 times Earth's radius and more than 17 times its mass. Around other stars, that empty interval is much occupied by several planets. This has got a minor gap between two neighbouring sizes. It covers an enormous range of possible worlds. Earth has a radius of about 6,379 kilometres. Neptune's radius is roughly 24,600 kilometres. A planet with twice Earth's radius may sound as though it should be halfway between them. Planetary size does not work by choosing a medium cut between a small one and a large one. Radius measures the distance from the centre to the surface. Volume increases with the cube of the radius. A planet with twice Earth's radius has about 8 times Earth's volume. A planet with 3 times Earth's radius has about 27 times the volume. Mass varies even more because planets of the same size contain different materials. Rock, iron, water, and hydrogen do not have the same density, but also behave differently under pressure. Two planets with equal radii have very different masses, surfaces, atmospheres, and internal structures. This means the region between Earth and Neptune holds several distinct kinds of planet. There can be dense rocky super-Earths, water-rich worlds, planets with rocky cores with deep atmospheres, and smaller versions of Neptune. Astronomers may group them together when discussing science, but nature has not placed a clear label on each one. Kepler's observations show that planets in this range are among the most frequent products of planet formation, at least on the close orbits that we should be measured most effectively. MASS is the planet detection agency for large populations of planets between roughly 1 and 4 Earth radii around sun-like stars, while surveys of smaller red dwarf stars find similarly high occurrence rates. The exact numbers depend on stellar type, orbital period, and the selected size boundaries. The overall result is consistent. Planets between Earth and Neptune are not rare transitional objects. They form a major part of the planetary population. That discovery changed a basic assumption. Before exoplanet surveys, it was easy to imagine that planets naturally fell into the same groups seen around the Sun. Small rocky worlds formed in the neighbouring system. Large gaseous worlds from farther out, where colder conditions allow planetary cores to collect enough material to capture large atmospheres. Earth and Neptune appear to represent two separate outcomes, with little reason to expect many planets between them. The galaxy did not follow that convenient arrangement. Kepler found systems containing one planet after another within the system's range. Some stars have compact families in which several planets orbited closer to their star than Mercury orbits the Sun. In those systems, a planet might be 1.5 times Earth's radius, followed by another twice Earth's radius, and a third slightly smaller than Neptune. The orbital periods could be measured in days rather than months or years. One useful example is the Kepler-20 system. Several of its known planets orbit within the distance separating Mercury from the Sun. Kepler-20b has a radius of about 1.9 times Earth's radius, and a mass close to 10 masses. Measurements suggest that it is unusually dense, and may have a mainly rocky composition, despite being larger than the radius at which many planets begin to show evidence of impact layers. It is a reminder that statistical boundaries describe populations, not strict rules for every individual world. Another system may contain planets of nearly the same size with much lower densities. Those worlds need only a modest amount of hydrogen and helium to appear significantly larger during transit. Gas occupies a great deal of space without or amount of mass. The planet can therefore be mostly rock and ice, while its measured radius is strongly affected by light outer atmosphere. Consider a rocky core several times more massive than Earth. It has almost no atmosphere. Its radius may remain below 1.5 Earth radii as gravity compresses the rocky matter inside it. With that same core of atmosphere containing only 50% of the planet's total mass, the planet's apparent radius can increase dramatically. The atmosphere is not massive compared with the interior, but it extends high above it. This creates a close situation. A relatively small difference in atmospheric mass can separate two planets that look very different to a transit telescope. One appears as a compact super-Earth, the other appears as a larger sun Neptune. Deep inside, They may contain similar rocky cores. For a while, Kepler's planet-size distribution seemed to form a broad rise through this region. Improved measurements later revealed more structure. California Kepler survey combined Kepler observations with detailed measurements of the host stars. Planetary radii depend directly on stellar radii, so better information about the stars produce better information about their planets. The survey examined more than 2,000 Kepler planets and found a density between about 1.5 and 2 Earth radii. Planets smaller than this gap formed one group, while planets around 2 to 3 Earth radii formed another. The shortage between them became known as the radius gap or radius barrier. After correcting for detection effects, the two groups appeared with roughly similar intrinsic frequencies. The word valley is useful because the region is not completely empty. Astronomers do find planets inside it. Kepler 20b is one example near or beyond the boundary, depending on how the category is defined. The important feature is that planets curl as frequently there in the region below or above it. Imagine arranging thousands of planets in containers according to radius. The first container begins filling with worlds close to Earth's size. The numbers remain high as the radii increase. Near 1.5 to 2 Earth radii is thick. Beyond the dip, another large group appears around 2 to 3 Earth radii. The result looks less like one continuous family and more like two related populations. The smaller population is often described as rocky super-Earths. These planets are usually close enough in size to Earth, but higher than silicate rock and account for much of their mass and radius. The larger population is often called sub-Neptunes or mini-Neptunes. They generally require lower density material, such as hydrogen, helium, water, or other volatile substances, to explain their measured sizes. Earlier work using planets with both mass and radius measurements had already suggested a transition near 1.6 Earth radii. Statistical analysis found that most planets at or above that size would not be explained as simple mixtures of iron and silicate alone. Larger planets were increasingly likely to contain substantial volatile layers. This does not mean every planet below 1.6 Earth radii is an Earth-like rocky world, or that every planet above it is a small Neptune. The composition depends on mass, temperature, atmospheric history, and materials available during formation. The water-rich planet have a lower density without possessing a hydrogen-dominated atmosphere. An iron-rich planet can remain rocky at a larger radius than expected. Measurement uncertainties can also move a planet from one side of the boundary to the other. Still, when thousands of worlds are considered together, acting as strain, something prevents large numbers of close-orbiting planets from remaining at intermediate sizes. The most widely studied explanations involve atmospheric loss. Young stars are active, emit strong X-rays and ultraviolet radiation, particularly during the first part of their lives. A planet orbiting nearby receives a heavy dose of this high-energy radiation. The Earth's atmosphere heats, expands, and may escape into space. The effect is strongest for planets with weak gravity, close orbits, and extended atmospheres. A massive planetary core can hold gas more effectively than a small one. A distant planet receives less radiation than a near-Earth planet. A compact atmosphere is harder to remove from one that's already swollen by heat. Suppose two young planets begin with similar looking cores and hydrogen-rich envelopes. One core is large enough to retain most of its gas. The other is slightly smaller or closer to the star. Its atmosphere escapes. As the gas disappears, the planet's observed radius decreases until the remaining rocky core is exposed. The two worlds may have begun with only moderate differences. After atmospheric loss, one remains a sub-Neptune, while the other becomes a bare super-Earth. Proto-evaporation models predicted a valley of this kind with real features clearly measured. These models show that atmospheric erosion does not reduce every planet smoothly to an intermediate size. Instead, planets tend to separate into two outcomes. The atmosphere may survive because the core's gravity can hold it. The thin atmosphere may be removed completely. Planets that lose their gas shrink to the size of their rocky cores. Planets that contain several percent of their mass of gas remain much larger. The intermediate stage does not necessarily last long enough to produce a large permanent population. One model found that atmospheric erosion would gather planets in two broad planets, with bare rocky cores around 1.3 Earth radii and gas-bearing planets around 2.6 Earth radii. In this explanation, much of the skeleton occurs during the first 100 million years, when stars produce especially strong high-energy radiation.
Underground disruptions. The way to train a dreamer.
What does it cost you when you just keep going and push through? I like that with the old thing, jumping through the corner, running on the corners, running with the school, but they're like mobbing away with your pleasure, step by success, and so on. And stop trophies. And I said with our showing your diamond, someone comes to show you, and you go through it, it's cool, like what do you like, like what really like, time of kids, time of Harry, and a bit of time to play home the next, or walk the dog, and it's like, where's that in the diamond? I said, well, it's embarrassing to have at the time of your life and play the school, time was everything in your life. I said, well, so everything else in your life, it's a very so much. So these disrupt this concept of play yourself first. And so on Sunday night, you sit down, you and your wife together, play yourself, decide that where's the stuff that we want to do, urges to go to your life, the urgent stuff doesn't always get the good news. You get tricked into thinking, I'm not going to slide them out.
There is another leading explanation called core-powered mass loss. It does not rely on greenhouse rays and ultraviolet radiation from the star. Instead, it uses heat stored inside the young planet. Planets are hotter than before. Material collides, compresses, melts, and releases gravitational energy. The rocky core surrounded by an atmosphere cools over time. Tuning outward can push the atmosphere away, especially if the gas is only high. In this model, the planet itself supplies much of the energy needed to remove its envelope. Small cores may lose their gas, larger cores retain it. Calculations show that core-powered mass loss can also reproduce the location, shape, and slope of the observed radius value without requiring photo-evaporation to do all the work. The two mechanisms are not mutually exclusive. The young planet can be heated by its interior while also being exposed to energetic radiation from the star. Both processes may contribute, with their relative importance varying between planets. Distinguishing them requires more than noticing the gap. Astronomers study how the value changes with orbital period, stellar mass, age, and the amount of energy planets receive. Photo-evaporation and core-powered mass loss can make different predictions about these relationships, although the predictions overlap in several areas. Crude stellar measurements have shown that the valley is not a fixed horizontal line at one radius. Sufficient changes with orbital distance and host-star properties. Around lower mass stars, the separation tends to occur at smaller planetary sizes. This may partly reflect the formation of smaller planetary cores around smaller stars, as well as differences in their radiation histories. The valley also changes across orbital periods. Very close to the star, small rocky super-Earths are common because atmospheric loss is efficient. In somewhat longer periods, more planets retain gaseous envelopes, and sub-Neptunes become more prominent. Analyses of the full-Kepler data set indicate similar to the distribution is strongest with a limited range of close orbital periods rather than remaining identical at every distance. This helps explain why the planets found by Kepler are not simply a set of worlds that fall in their present sizes. Their current radii contain a record of both formation and later evolution. The initial core matters, the amount of gas collected from the surrounding disk matters, the time at which the disk disperses matters, on its orbit matters, the star's early activity matters, the internal heat of the planet matters. determine whether the final world is below or above the obvious value. The most common planets in the galaxy will therefore be common, not because nature repeatedly builds one standard object, but because several ordinary processes repeatedly move into the same general size range. Rocky cores commonly grow beyond Earth's mass. Before the gases disappear, many of them require atmospheres. Some retain those atmospheres and become sub-Neptunes. Others lose them and become superplanets. Collisions can add mass smaller than new planets. Migration can place planets in close orbits where atmospheric escape becomes stronger. Different histories produce a large collection of worlds between the sizes represented in our solar system. Neptune itself sits far above most of the population. It has a large envelope and a mass exceeding 70 worlds. Many sub-Neptunes are considerably smaller, perhaps containing only a few Earth masses of rock beneath a relatively light atmosphere. They are not necessarily fellow Neptunes waiting to grow. They may be a stable and extremely common outcome in their own right. Earth lies below the normal sub-Neptune population. Its atmosphere contributes almost nothing to its overall radius. Removing Earth's eye would make very little difference to the planet's measured size. The same is not true for a world with a hydrogen and helium envelope representing 1 or 2% of its mass. Remove that gas and the planet can shrink significantly. This distinction helps clarify why the gap in our solar system is mysterious. We're not really missing a planet on the radius halfway between Earth and Neptune. We're missing both closely related populations that generate many complex systems. There is no known rocky planet with several times Earth's mass. There is no nearby sun Neptune with a rocky core and a thick hydrogen-rich envelope. Uranus and Neptune are much larger and farther from the Sun. Mercury, Venus, Earth, and Mars all remain below the common exoplanet size range. The contrast becomes even more noticeable when the orbital arrangements is considered. Many super-Earths and sub-Neptunes orbit within intense Earth-sun distance. Some systems contain suborbit. Our corresponding region contains Mercury, and then a large empty space leading to the Sun. Detection bias makes this comparison appear more dramatic because close-orbiting planets are easy to find. A planet with a 10-day orbit produces frequent transits, a stronger radial velocity signaling the same planet to a 10-year orbit. Surveys naturally collect more complex systems. Even after researchers have dropped those biases, however, the underlying population remains substantial. Telescopes did not invoke the super-Earths. They simply noticed the worlds our early influence had been least able to see. There may also be many super-Earths in larger orbits that current surveys have missed. Such planets transit less often and have a lower chance of crossing their stars from our viewpoint. Long-term radial velocity surveys can find some of them, while gravitational microlensing can detect planets at larger distances from their stars, but the census becomes less complete as orbital periods increase. The phrase, most common worlds in the galaxy, should therefore be used with care. Strongest evidence for the abundance of super-Earths and sub-Neptunes on relatively short orbits. Determining the most common planet across every size and orbital distance remains difficult, because no single detection method sees the entire population equally well. Nevertheless, the central result is not dependent on declaring one exact winner. Planet formation produces a great many worlds between Earth and Neptune. Our system does not contain them. There is an interesting possibility hidden inside that absence. Earth may be small, not because rocky planets naturally stop growing at one Earth mass, but because something interrupted the supply of material in our own system. Mars may be unusually small for the same reason. Innocent super-Earths may be connected to the limited mass of unfortunate small planets. Alternatively, the inner solar system may also contain larger worlds. It could have moved inward and fallen into the Sun. It could have collided, broken apart, or been absorbed during the violent early stages of planetary formation. The current planets would then be survivors rather than the original population. Jupiter may also be involved. If its core formed early, it could have disrupted the inflow of planets and other solid material through the disk. The inner region would have received less material. preventing Earthlings and members from reaching super-Earth. In another set of models, Jupiter's migration altered the distribution of young planetary bodies in clear parts of the system. To see how that sequence would produce several super-Earths in one system and none in another, we need to return to the period before there were any planets at all. The young star sat inside a broad, rotating disk of gas and dust. The disk was not an accessory to the star which formed. It was not so event. Stars begin inside cold molecular clouds, where regions of gas and dust can collapse in their own gravity. As the material falls inward, even a small amount of initial rotation becomes important. Collapsing cloud spins faster, while they're like a skate of rolling their arms, although the cloud is much larger and has no interest in receiving applause. Most of the material gathers near the centre and feeds the glowing star. The rest spreads into a flattened disk around it. These protoplanetary disks can extend far beyond the region where the final planets will orbit. They contain mostly hydrogen and helium gas, with a much smaller amount of solid material made from rock, metal, carbon-rich compounds, and ice. Observations of young stars show that disks are generally dominated by gas, even though the dust is easier to see at any wavelengths as far as most of the solid ingredients from planetary cosmology. Planetary systems are therefore a side effect of star formation, assembled from the material that did not originally fall into the star. At first, the solid pieces are extremely small, many are finer than household dust. They move through gas that is itself orbiting the star, and their motion is controlled by gravity, collisions, turbulence, electrical forces, and drag. None of this resembles a set of tiny planets lightly circling in separate lanes. The disk is active, material falls inward, gas spreads outward in some regions, winds remove matter, temperatures change with distance and with time. The young star broadens, flies, and sends radiation into the surroundings. Within this changing environment, dust grains collide. Some collisions are too fast and cause the grains to bounce or break apart. Gentle encounters allow particles to stick, especially when the surfaces are coated with ice, or contain materials that can absorb some of the impact. Small aggregates form, then larger ones. Dust becomes grains. Grains become clusters. The clusters can grow into pebbles. NASA's basic description of planet formation follows this route from microscopic dust to pebbles, larger rocks, planetesimals, and eventually planets, while emphasizing that many collisions destroy material as well as building it. The process sounds simple when described in modern sciences, but much less simple when anyone asks how a fluffy clump of dust becomes an object several kilometers across. Small grains are strongly coupled to the gas. They move with it and meet one another at manageable speeds. Larger particles react differently. Pebbles can drift rapidly toward the star as the gas does not orbit at exactly the same speed as solid objects would in a vacuum. Gas pressure provides some support against gravity, so the gas travels slightly more slowly than the natural orbital speed. A solid particle therefore feels a headwind. It loses orbital energy and moves inward. This radial drift can be alarmingly efficient. A pebble that took a long time to grow may spiral inward before it has the opportunity to become part of a larger body. Planet formation has therefore overcome a problem that sounds familiar in many forms of construction. Building materials keep moving the site. Collisions create another obstacle. As particles grow, they often strike one another too quickly to stick. They bounce, fragment, or erode. This is sometimes called the bouncing barrier or fragmentation barrier. The neat sequence in which every grain is scattered and joins a larger object is not realistic. Much of the material is recycled with material. Modern models often solve the particle problem by allowing pebbles to gather into locally dense regions. Turbulence and interaction between solids and gas can concentrate particles under suitable conditions. The process called the streaming instability produces clumps dense enough for their own gravity to take over. Instead of building a kilometre-sized body one collision at a time, the cloud of pebbles can collapse into a planetesimal. A planetesimal is a solid object large enough in diameter to become important in its growth and interactions. Depending on the model, newly formed planetesimals may be tens or hundreds of kilometres across, rather than beginning as tiny rocks and climbing smoothly to quickly possible size. Reviews of current planet formation theory identify gas drift, radial drift, streaming instability, planetesimal formation, and later accretion as connected stages, while noting that the preferred locations and efficiencies remain active areas of research. Once planetesimals exist, gravity makes growth easier and more violent. A larger body can pull smaller objects toward it. Its effective collective power becomes greater than its physical surface, as gravity bends nearby clouds inward. This is called gravitational focusing. The larger object goes faster, which strengthens its gravity and helps it grow faster again. Some bodies begin to pull ahead of the surrounding population. This stage is known as runaway growth. It does not mean that young planets become emotionally overwhelmed and left home. It means that differences in size become amplified. The largest planetesimals collect material more efficiently and turn into planetary embryos. Eventually, the embryos disturb one another so strongly that growth becomes more regulated. They clear or control regions around their orbits and compete for the remaining material. This is often called oligarchic growth. The several dominant embryos share control of the disk, rather than one object immediately consuming everything. Near the young sun, those embryos may have been roughly moon-sized or Mars-sized before the gas disappeared. Afterward, they continue colliding for tens of millions of years. Earth's final growth probably involved several major impacts, including the collision force which produced the moon. Rocky planets are not assembly of the delicacy of hand-watching. They are built through impact energetic enough to melt large portions of them, strip atmospheres, mix materials, and occasionally turn two proxy worlds into one extremely hot world surrounded by debris.
When it's time to study a distance, it's time for mathematics. For everything we need to know the way our whole self progresses against each other. Approach changes from every channel, working with this spot. It's a very specific researchers who get some features. Secret visits to a whole new level. Switch to Shopify. Keep doing it right. Every video, every trailer, every intro, in many cases, we'll keep pushing it further. The eighth generation of this is coming in the next half an hour, and it's 194% stronger than before. Soon the relaunch of this Plus, something very exciting is about looking at this year. But all of that takes serious investment in research and development, into doing stuff, more distribution centers, EU and AIM, reducing due time, and the cost for our customers go up. That's why we're proud of it. Now, this is fortunate to be able to take out our
The location inside the disk strongly affects what material is available. Close to the star, temperatures are high. Water and many other volatile substances remain as vapor in solid ice. The available grains are mainly refractory materials that can survive heat, including silicate rock and metal. Farther out, the disk becomes cold enough for water to freeze. The transition is commonly called the water snow line or ice line. Beyond that line, ice adds a large amount of solid material. The growing body can collect rock and frozen water together, increasing the supply of which a planetary core can form. Other compounds fuse at still greater distances, creating additional chemical boundaries. The snow line is not fixed. As the young star and disk evade, temperatures change, and the line can move. Heating from the star, friction within the disk, and local structure all influence its position. Even so, the basic difference between warmer regions and colder regions helps explain why the solar system has rocky planets near the sun, and volatile rich giants far away. NASA's overview of planet formation simply distinguishes the warmer and the disk, where rocky worlds grow, the colder regions where ice increases the amount of available solid material. It does not explain everything. Exoplanets have shown that planets rarely remain where simple temperature practices they should have formed. Core accretion is the general framework for building those planets. The solid core grows first through a collection of planetesimals, pebbles, or both. That core becomes massive enough to let plenty of gas run into the disk and bind a substantial atmosphere. At first, the envelope may grow slowly because it is hot and steady. As the atmosphere cools, it contracts and makes room for more gas. If the core and envelope reach suitable conditions before the disk disappears, gas accretion will accelerate dramatically, producing a giant event. Timing is crucial. Protoplanetary gas disks usually do not last indefinitely. Much of the gas is lost within a few million years, although rare long-lived disks are known. Giant planets must therefore form their cores quickly enough to capture gas before supplies are removed. NASA's overview notes that Jupiter and Saturn are built before gravity within the first roughly 10 million years, while the final assembly of rocky planets continued for tens of millions of years. The core that grows too slowly may miss the opportunity and end as a super-Earth ice-rich planet rather than a gas giant. A core that reaches several Earth masses and captures a modest atmosphere may become self-watching. It's the larger core will trigger runaway gas accretion and become something closer to Saturn or Jupiter. This helps explain how the Earth's direction range is so heavily populated. Growing a core of several Earth masses may be common. Capturing a small envelope may also be common. Reaching full giant planet status is harder as it requires the right mass, location, gas supply, and timing. There are two main ways for a young planetary core to get solids after the earliest planetesimals appear. They accrete planetesimals, meaning it gains mass by colliding with larger solid bodies. It can also accrete pebbles that drift through the disk. Pebble accretion can be extremely efficient under the right conditions. A pebble passing near an embryo feels both gravity and gas drag. Gravity pulls it toward the embryo, while drag removes enough energy to prevent it from simply flying past. The embryo can collect material from the void region, allowing growth to proceed much faster through occasional collisions with planetesimals alone. The rate depends on the pebble supply, the thickness of turbulence in the disk, the embryo's mass, and its distance from the star. A small embryo may capture very little. Once it becomes sufficiently massive, its reach increases and the growth will accelerate. This produces an important competition between the speed of growth and the speed of movement through the disk. Pebbles themselves move in inward, which means material from cold outer regions can be delivered toward warmer inner regions. When icy pebbles cross the snow line where water ice can vaporize, even smaller rocky particles are formed. This changes both the amount and composition of solid material available at different locations. The system will stop the wood flow pebbles and feed rapidly growing planets. Several embryos will reach super-Earth masses before the gas disk disperses. When they also migrate inward, it can become part of the compact chamber close to the star. The system will weaken for the image of smaller planets. An early giant planet core can also change its supply. As a growing planet becomes massive enough, its gravity disturbs the gas, creating pressure mark outside its orbit. Inward drifting pebbles can become trapped in that bubble instead of continuing past the planet. The mass at which this occurs is called the pebble isolation mass. This is a turning point for both the growing planet and the rest of the system. The planet cuts off its own pebble supply, but it also starves the disk. Jupiter's core reached pebble isolation early, could have reduced the amount of solid material delivered to the young terrestrial planets. Earth, Venus, Mars, and Mercury were then fed from a limited reservoir, rather than receiving a continued supply of those super-Earth systems and known elements. The exact history remains debated. Pebble isolation depends on disk conditions, and researchers differ over how much material Jupiter could block when its core formed, whether other processes carry solids across the barrel. The idea is attractive, as it features of our system, the presence of an early giant planet and the absence of close super-Earths. It also shows that planets do not grow independently. The first large core can change what meteors are able to become. Planets open a gap in the gas, can trap dust, can disturb neighboring embryos, can redirect pebbles and planet essays, can alter the chemical material which can exist. The final architecture depends not only on the total amount of matter, but on which object grows first and where it grows. Observations of protoplanetary disks provide direct evidence that young systems contain structure. Telescopes have imaged rings, gaps, spirals, bright concentrations and asymmetries of disks around nearby stars. Some gaps may be carved by young planets, while others can arise from snowlines, changes in dust properties, magnetic effects, or pressure variations. The gap is therefore not an automatic birth announcement. These features show that disks are not smooth, featureless pancakes. Hubble, however, and other observatories have revealed disks with lanes and rings that may mark location to where material gathers, or where fallen planets or influence of lesser elements. One famous image from hangout showed the disk around the young star Tauri, divided into a striking series of bright and dark rings. The star was no more than about 1 million years old, but its disk already displayed extensive structure. The observation encouraged the idea that planet formation, or at least the concentration of material needed for it, may begin earlier than older models have assumed. Not every ring contains a planet. Dust can collect in pressure bumps without a planet being present. Chemical changes can alter membranes and location. Even so, the presence of structure suggests that the building process is organized by local traps, barriers, flows. These preferred locations will help embryos grow. Pressure maximum slows or halts radial drift, allowing solids to collect instead of vanishing toward the star. Snowlines can change particle stickiness in the amount of solid material. Disk edges and regions will change in turbulence and concentrate pebbles. Planet formation may therefore begin at particular locations rather than occurring evenly across the disk. Modern reviews emphasize that planetesimal and planetary growth is likely concentrated in favorable zones, while much of the material elsewhere may remain at pebble size. Once an embryo becomes large, it affects the gas around it, and the gas affects the embryo in return. The planet raises density values in the disk. These waves exert gravitational torques, twisting forces on the planet. The forces from the inner and outer portions of the disk are to cancel perfectly. The imbalance changes the planet's orbit. For low-mass planets, this interaction is usually called type-1 migration. It can move an embryo inward on timescales shorter than the lifetime of the gases. Under some disk conditions, migration can slow, stop, or even reverse temporarily. Inward motion is a common outcome. A giant planet can carve a deeper gap and migrate to a different regime, traditionally called type 2 migration. Modern simulations show that the boundaries between migration types are not always simple, and the speed depends on the disk, planet, or whether gas crosses the gap. The important point is that growing planets are not anchored to their birthplaces. This mobility solves several puzzles and creates several more. Explain what Jupiter's probably did not form at their present spiritual distances, and deliver icy material to a living system, collect embryos into compact resonant chains, can also reveal planets by carrying them into the star. Models that combine pebble accretion and migration effect produce natural split. Embryos that grow within a disk reach super masses do not become gas giants. They migrate inward and collect in other disks emerge. Embryos forming farther up and grow larger and capture gas if they receive enough pebbles quickly. Simulations show that the balance between pebble flux, growth, and migration will create compact super-Earth systems, giant planets, or mixtures of both. This makes the frequency of super-Earths easier to understand. A disk does not need to be filled with several finished planets close to its star. It build embryos over a wider region, even with drifting pebbles, and allow their interaction with the gas to move them inward. Several worlds collide with the star, contracting the fluids, and continuing. The inner edge of the disk provides a natural stopping region. Close to the young star, magnetic fields and high temperatures can reduce the gas density and create a cavity. Migrating planets may store there. Later arrivals can contract on them first, producing a chain of closely spaced planets. While the gas remains, the disk can damper eccentricities and inclinations, keeping the orbits fairly circular and flat. The system may look stable. Once the gas disappears, that support is removed. Some chains survive, others become unstable. Planets collide and merge, reducing the number while increasing their masses. Orbits spread apart, the resonances grow. A system that began with many small embryos reached with a handful of supernovas. Our solar system may have taken a different route as the material supply, the timing of Jupiter's growth, the disk structure, and the direction and speed of migration differed. It may also pass through its own migration before the spiral of rocky planets formed. The available evidence does not identify one acute moment when a normal super-Earth system became more unusual one. What it does show is that planets are built inside a moving environment. Dust drifts, pebbles cross chemical boundaries, embryos compete, cores capture gas. Early planets reorganize the supply available to later ones. Throughout all of this, the disk continues building the objects it is creating. The planet can begin far from the orbit where astronomers eventually discover it. In many systems, that movement is not a small adjustment. Carry a growing world as a large part of the planet-forming disk is close enough to its star that an entire year lasts only a few days. This movement is called planetary migration. The term sounds calm, as though the planets have reviewed several orbits and decided that the system is best transformed. The real process is driven by gravity. A planet pulls on the disk around it, and the disk pulls back. Because the forces on the inner and outer sides of the planet are not perfectly balanced, the planet can generally lose orbital energy. Most of the time, a relatively small planet loses energy and moves inward. To understand why, picture a young planet embedded in a broad disk of gas. Material closer to the star moves around the star faster than the material further out. The planet's gravity disturbs both sides of the disk, creating spiral-shaped flows. The inner disk tends to pull the planet forward, which adds orbital energy. The outer disk tends to pull it backward, which removes orbital energy. Those forces were equal, and the planet would remain in roughly the same orbit. The usual amount. In many common disk conditions, the outer torque is stronger, so the planet gradually spirals toward the star. When an object only a few times than Earth, this is known as tight migration. It can happen surprisingly quickly. In some conditions, the young super can move a substantial distance in less than a million years. That is proof compared with the life of gases, which may persist for several million years. The planet therefore has plenty of time to move before the disk disappears. The exact speed depends on the planet's mass, the density and temperature of the gas, and the thickness of the disk, and the energy to moves through it. Migration is not a simple conveyor belt run at one speed. A planet will move inward rapidly, slow down, pause, move outward for a while, or change direction as the disk evolves. Regions where temperature or density changes sharply create migration traps. Near one of these locations, the inward and outward forces may balance. Growing planets can remain temporarily. Slow lines, changes in turbulence, and the inner edge of the gas disk may produce such stopping points. Temporal is the important word. The disk itself is changing. Gas is falling onto the star, spreading out within some regions, being heated, cooling, and escaping through winds. A balance that holds a planet in place early on and disappear later. Once that happens, migration begins again. This creates a system in which planets do not really form. They form while their surroundings are moving. Then they move through those surroundings, continuing to grow. The young planet migrates inward and cross regions containing different materials. Far from the star, collect ice-rich pebbles and cloudy teasers. Closer in, the environment becomes warmer and drier. Final planets may contain material gathered from a broad range of distances rather than only from the orbit where it's found. That makes the interpretation of exoplanets more difficult. Close-in planets with a large amount of water are what are called close to a star, which may have begun beyond snowline, collecting ice, and migrated inward. The dry, rocky planet might have formed later, or it might have lost water through heating, collisions, or atmospheric escape. Location does not always reveal origin. Migration also changes how quickly a planet can grow. As it travels through the disk, it encounters new supplies of pebbles and planetesimals. Instead of consuming any material in one way or the zone, it collects from a much wider path. This is especially useful for building super-Earths. In a simple model without much migration, the planetary embryo can eventually use up the solid material close to its orbit. Its growth slows because the local supplies can be cleared. A migrating embryo does not have that problem in the same way. It continues entering regions where material remains available. Several embryos can grow and migrate at the same time. The first one to reach the inner part of the disk will stop near the disks at the edge. Another arrives behind it. When gravity begins to affect each other, instead of immediately colliding, the planets can become trapped in resonance. An orbital resonance occurs when the planet's periods form a single ratio. One planet may complete 3 orbits for every 2 completed by its neighbor. Another planet may settle into a 2-to-1 relationship. Each time the planets pass through certain positions, they give one another small but repeated gravitational fields. These repeated interactions can keep their orbits linked. The process often begins when the outer planet migrates inward faster than the inner one. The distance between them decreases until the pattern of their gravitational encounters begins to unravel. Once captured into resonance, they may continue moving together. A third planet may join the pair, and a fourth arrive. The result is a resonant chain containing several worlds on different orbits. This type of arrangement appears in both observations and simulations. Some known planetary systems still preserve clear resonant relationships. Others contain planets near simple ratios, suggesting that they may once have been in resonance before later interactions shifted their orbits. TRAPPIST-1 is one of the best known examples. 7 roughly Earth-sized planets orbit a smooth red dwarf star, and the system contains a complex chain of resonances. The outer planets complete their orbits as they keep their gravitational interactions coordinated. All 7 planets would fit well inside Mercury's reach at the Sun. TRAPPIST-1 does not contain massive large super-Earths. It demonstrates how the planets can migrate or assemble into a tightly packed configuration without immediately destroying one another. Other systems contain similar compact chains with planets larger than them. Chapter 223 includes 4 planets in an interesting arrangement. Their orbital periods follow a pattern that is difficult to explain through random placement. The system is generally interpreted as evidence that the planets migrated while the gases were present and became captured into resonance. During the disk phase, gas helps keep these chains stable. It reduces orbital eccentricity, which measures how stretched an orbit is, and adapts the planet's inclinations, never nearly the same length. The gas acts as a stabilizing influence while migration pushes the planets together. Then the disk disappears. Ultraviolet radiation and winds from the young star remove gas. Material also continues falling out of the star. Within a few million years, the main gaseous structure fades. The planets remain. The force that controls their migration and soften their orbits is gone. Some resonant chains survive this transition, others do not. The tightly packed group can become unstable after the gas is removed. Small gravitational disturbances build over time. Planets may move their resonances, cross one another's paths, and collide. Some are scattered into wider orbits, others fall toward the star, a few may be thrown out of the system entirely. Collisions between young super-Earths are common in many simulations. Two planets merge, producing one large world. The rocky interiors combine, although part of their atmospheres may be lost. Repeated collisions can turn a chain of numerous embryos into a smaller group of more massive planets. This helps explain why many observed systems include several planets that are close together, but not in exact distance. They may be survivors of an earlier resonance change, and current spacing records a period of instability after the gas disappeared. Planets often remain in nearly circular, nearly flat orbits, because the instability is not always violent enough to scatter them far apart. It's simply moved from a highly organized resonant arrangement to a looser but still compact system. The solar system's inner planets do not resemble that. Mercury, Venus, Earth, and Mars are widely spaced compared with many compact exoplanet systems. None is several times Earth's mass. No chain of planets orbits between Mercury and the Sun. The terrestrial planets are not arranged in a close resonance as expected from a group that migrated in together and remained there. This suggests that either the process did not occur here, or its results were immense. One possibility is that the young solar system never produced several rapidly growing inner embryos massive enough to make them efficiently through the gas. Migration becomes stronger as planetary mass increases. If the inner building blocks remain small where the disk was present, they may not have travelled very far before the gas disappeared. Later, after the gas was gone, those smaller embryos would glide over tens of millions of years and form terrestrial planets. In this scenario, Earth became large only after the main migration period ended. That would explain why Earth did not join contact with the Sun. It was not yet Earth, and the disk was capable of carrying that. The time depends on how quickly the inner planets receive solid material. A strong flow of inward drifting pebbles would build large cores early, producing migration of super-Earths. The limited supply could move smaller embryos that move slowly. Humans may have limited that supply by reaching carbonization in Earth. Once its growing core disturbed the gas strongly enough, it could have created a pressure barrier outside its orbit. Pebbles drifting inward from the outer disk would be left there while the continued between the Sun. If that happened early, the inner solar system would have been deprived of the material needed to build several massive cores while the gas was still present. The terrestrial embryos would remain small, the migration would be weak, they would finish growing only after the disk had dispersed.
The greatest ever summary ever was never
It's funny, Martha. This is where we went. This is really nice. Sorry. So simple.
Like anything I can only size body books or something. Nothing like that. I'm the honest. Well, I was going to get them. But don't think of the problem, huh? Well, you could have said 310 cups a year on average without even one.
Another possibility is that super-Earths did form and migrate inward, but they did not survive. In some models, the first generation of close planets spiraled into the Sun. They may have been lost because the inner edge of the disk did not provide a permanent stopping point, or because the edge itself moved inward as the star and disk emerged. The planet trapped at the inner edge is not necessarily the Sun. If the gas cavity shifts, the planet will follow it. Several planets pressing against one another in resonance can also push the innermost planet closer to the star. Eventually, the first planet will cross into an unstable region and be consumed. The next planet then becomes the innermost planet, but they also be pushed inward. In this process, an entire chain can disappear. This sounds dramatic, but falling into a star is not unusual in planet formation models. Many disks can produce planets already lost. The systems we observe are not a record of everything they've ever thought. They're a record of what's found. There's no direct evidence that the sun swallowed a chain of super Earths. The idea remains one possible explanation. Those planets existed very early. The material may have been absorbed so thoroughly that little obvious evidence remains. A more violent version suggests that the big migrating planets destabilized the very evaporation of small bodies near the sun. Collisions produced debris. Much of that debris spiraled into the star as a drag on the remaining gas. After this clearing event, terrestrial planets formed from material farther out. Such models attempt to explain not only the absence of super-Earths, but also the low mass of Mercury in Mars and the sharp outer edge of the inner planetary region. Reproducing features of our system, though they depend on assumptions about the timing and masses of the original bodies. There is another reason migration may behave differently there. Giant planets alter the movement of smaller planets. Jupiter and Saturn exerted strong gravitational effects on the disk and on one another. Formed early enough, their resonances and migration could have changed the distribution of gas and solids across the entire system. Small planets moving inward may encounter a region influenced by a giant planet. Its migration is slow or reverse. Embryos can be trapped outside the giant. Material can be scattered inward or outward. Resonant relationships among the giants can reorganize the disk. This means the absence of closer super-Earths may not be explained by one local event near the sun. They are connected to the history of planets that form much farther away. The fate of migrating worlds also depend on the type of star. While in small red dwarfs, the disk is generally less massive. The region where temperatures allow rocky planet formation lies close to the star. Orbital periods are shorter, and migration can gather planets in very compact systems. Because red dwarfs are the most common stars in the galaxy, their compact planetary systems contribute heavily to the number of known super-Earths and Earth-sized worlds. Around larger stars, disks can contain more material, potentially allowing cores to grow more rapidly. Some become gas giants, others remain in the super-Earth and some Neptune range, depending on when they form and how much gas they capture. Stellar magnetic fields also influence the disks at average. Young stars rotate and interact strongly with nearby gas. Inner disks can even truncated when a magnetic field controls the flow. Migrating planets can collect near this boundary. The location of that boundary helps determine the shortest orbital periods in the planet system. If the inner edge lies close to the star, planets may be locked on orbits lasting only a day or two. As the star evolves, the edge can move, and the planets may move with it. Some planets become so close to their stars that tidal forces dominate their later evolution. The planet raises a tidal bulge on the star, and the star raises one on the planet. These bulges are not always aligned perfectly with the line connecting the two objects. The resulting forces exchange energy and angular momentum. The closer the planet, tides can gradually make the orbit smaller and more circular. The planet's rotation may become synchronized, even the same side facing the star at all times. This is called tidal locking. The planet that migrated inward during the disk phase may therefore continue moving long after the disk is gone, though much more slowly. Over billions of years, tides can travel closer to the star. In extreme cases, the planet may cross the Roche limit, where the star's tidal forces pull it apart. Astronomers have found worlds with orbital periods of less than 1 Earth-day. These ultra-short period planets are often rocky and extremely hot. Many may be stripped cores of former subdivisions. Others may have formed through collisions or lost their atmospheres after migration brought them close to their stars. Their surfaces can reach temperatures high enough to melt rock. The permanent bayside can contain lava, while vaporized minerals form thin atmosphere. These are called super-Earths because of their size or mass, not because they offer improved living conditions. Migration can also stop well before a planet reaches such an extreme orbit. Several planets may remain at distances where their years last 10, 20, or 50 days. These worlds are still much closer to the stars than Earth is to the Sun. A planet in a 10-day orbit around a sun-like star receives intense radiation. able to thick atmosphere and lose part or orbit. This leads vibration directly to the radius magnet discussed earlier. Planets are moving with one disk exists. After the disk disappears, radiation and internal heat change their atmospheres. Some remain sub-Neptunes, others become bare super-Earths. Common close-in populations observed by Kepler are the combined result of formation, migration, collisions, and atmospheric life. No single stage can explain everything. A planet's final radius may depend on how large its core grew before migration. Its present orbit may depend on resonance with neighbors. Its atmosphere may depend on how close migration carried it to the star. Its survival may depend on whether the system became unstable after the gas disappeared. Even planets that are very far may have experienced a complicated journey. The orbital planes of the main planet systems are remarkably flat. Several planets transit the same star, which can happen only if their orbits are aligned closely enough with our line of sight. This flatness is consistent with formation and migration inside a thin disk. The spacing also often follows a pattern. Neighboring planets tend to be separated by enough distance to avoid immediate instability. They remain far closer than the planets in our solar system. Many neighboring pairs lie just wide of exact resonances. This is what might be expected if the planets were originally captured into resonance, then moved slightly apart through tides, turbulence, or later interactions. Other systems are less orderly, contain planets on eccentric or inclined orbits, possibly because of stronger instabilities, giant planet interactions, or distant stellar companions. Migration is therefore common, but does not use one standard architecture. Provided relatively with planets, the final result depends on everything during and after that movement. The system can finish with a hot Jupiter close to its star and a few neighboring planets. It can retain a resonant chain of Earth-sized worlds. It can produce several non-resonant super-Earths and sub-Neptunes. It can use its inner planets entirely. It can also end with widely spaced terrestrial planets and distant giants, as our solar system did. A lot result of this to repair its history. Our system avoided placing a large planet close to the Sun. Jupiter did not remain in the region, although it may have moved substantially during its formation. Saturn formed soon after effect Jupiter's path. The supply of material to the terrestrial zone remained limited. The surviving inner planets finished growing after much of the gas had vanished. Whether all of those events were necessary is still uncertain. What is clear is that the movement of planets cannot be separated from the history of others and super-Earths. In many other systems, migration is a delivery mechanism that carries growing cores inward, gathers them into chains, and gives them access to additional material. In our system, something interrupted that delivery, redirected it, or removed the planets that completed the journey. The most obvious object capable of changing the traffic across the solar system is Jupiter. Formed early, became massive, disturbed the disk, and influenced almost every region around it. Whether it protected the inner planets, starved them, scattered their predecessors, or simply had to grow at the right moment as the next part of the problem. Jupiter is often described as Earth's guardian. The usual story is that its enormous gravity controls the outer solar system, throwing dangerous comets and asteroids away before they can strike us. It is an appealing picture. Jupiter becomes a large, strong security guard standing beyond the asteroid belt, keeping an eye on suspicious objects and occasionally asking the planet where it is going. The actual situation is less reassuring. Jupiter can remove objects from the solar system, but it can also redirect them toward the inner planets. Its gravity can capture comets into shorter orbits, disturb asteroids, create unstable regions, and send material across Earth's path. Whether Jupiter reduces or increases the impact risk depends on the original population of objects. Like orbits, Jupiter's mass, and the period of solar system history will be considered. The same uncertainty applies when we ask whether Jupiter prevented the formation of super-Earth. It acted as a guardian, not necessarily by protecting the fixed Earth from danger, and instead we protected the solar system from receiving too much building material. That would make it less like a shield and more like someone who quietly cancelled several deliveries before Earth and large motors.
Calories left on meal deal. Save a delicious 60 pounds on my convenience save when bought with any new laptop. In text scam sparkle, I can say this sentence. Taste the discount code software and calories.
Until Tuesday, these deals, deals, and more deals at 40% off.
Jupiter contains more mass than all the other planets combined. Its present orbit lies about 5 times farther from the Sun than Earth's orbit, and it takes almost 12 years to complete one circuit. Those facts describe the planet today. They do not tell us where it began, how quickly it formed, or how far it moved while the gases were still present. Timing matters because a young Jupiter will influence the movement of planets planetary worlds of gas. Jupiter that formed after the terrestrial planets were mostly the Sun have arrived too late to determine their masses. A Jupiter that formed during the first million years could have changed the supply of material, for Earth was much more than a collection of small bodies. Meteorites provide some of the strongest evidence that Jupiter began growing very early. Meteorites do not remain the same as chemical composition. When scientists examine certain elements within them, the samples divide into two group families. These are often called the non-carbonaceous and carbonaceous reservoirs. The differences suggest that parent bodies form from material in separate regions of the young solar system. The separation appears to have lasted for several million years. That is surprising because gas, dust, and pebbles in a protoplanetary disk normally move in mix. Something must have created a barrier between the two reservoirs. One influential interpretation is that the growing core of Jupiter produced that barrier. Isotopic dating led researchers to propose that Jupiter reached roughly 20 Earth masses within the solar system's first million years. Then it grew more slowly, reaching around 50 Earth masses after several million years, before rapidly collecting most of its gases and oil. The precise growth history depends on the model. The meteorite evidence strongly supports an early separation of the disk from the system of Jupiter forming quickly. At first, 20 Earth mass object did not look like Jupiter we see today. It would have been a large planetary core surrounded by gas, still far below its founding mass. Even so, it already eroded the structure of the disk. Pebbles drifting toward the Sun will lose orbital energy as they move through gas. Left undisturbed, a large supply of the outer disk across the region where Jupiter formed and continues toward the terrestrial zone. Those pebbles can feed embryos near the Sun, allowing them to grow quickly enough to become super Earths before the gas disappears. A sufficiently massive core changes the gas pressure around its orbit. Material immediately outside the planet can collapse near a pressure maximum. Pebbles drifting inward become trapped there because the pressure structure removes the headwind that would be causing them to lose orbital energy. Once the core reaches this pebble isolation mass, the flow of solids toward the other system falls sharply. The planet is not built a solid ball. Gas may still cross its orbit, and some dust or tiny T-samples may find those through. Even so, greatly reduce the delivery of pebble-sized material. Models of pebble evolution show that this isolation is a natural consequence of a growing core becoming massive enough to disturb its disk. This gives Jupiter a possible role in the massive super-Earth problem that does not require it to destroy anything. Imagine two young planetary systems with similar disks. In the first, when a giant planet core forms early, pebbles continue drifting inward for several million years, Embryos in the inner system receive a steady supply. Some grow to several times their mass while the gas is still present. They migrate toward the star and form a compact chain of super-Earths and sub-electrons. In the second system, the outer core grows quickly and reaches proper isolation mass. Liquid flow is reduced. Embryos closer to the star may share the material already present there. They remain relatively small during the gas disappears, so their migration is weaker. After the gas disappears, they collide over tens of millions of years and produce a few rocky planets. The second system begins to resemble ours. In that version of events, Jupiter did not steal a super-Earth, preventing the solar system from collecting enough material to build one. Earth, Venus, Mars, and Mercury are comets in a limited budget. That limited budget may explain several features at once. Earth beings become substantial rocky planets, and neither reach several Earth masses. Mars remains relatively small. Mercury is smaller still. There is almost no planetary mass inside Mercury's orbit, even though many exoplanet systems contain several worlds in the Green region. The reduction of the presence of planets is an attractive explanation, as all of these features involve a shortage of solid material. It also connects the terrestrial planets to Jupiter's early growth without requiring Jupiter to pass directly through their present orbits. There are difficulties, of course. The effectiveness of the barrier depends on the structure of the disk and the sizes of the solids. Tiny dust grains can remain strongly coupled to the gas across regions that trap large heavens. Turbulence can go on sometimes through. Large planetesimals are not stopped in the same way. Material may also move through gaps along complex planets. Jupiter's core would not have turned the outer disk into a sealed warehouse with a sign and no deliveries beyond the point. The question is how much the supply was reduced and whether the reduction occurred early enough. Meteorite reservoirs add another complication. Jupiter must have separated the material efficiently enough to preserve their isotopic differences. Some exchange still occurred. Earth contains water and other volatile substances that probably came partly from material originating farther from the sun. A perfect barrier would make that a little difficult. The likely answer is that Jupiter's influence was strong and incomplete. Restricting the main flow allowing small quantities of outer materials to reach the terrestrial region through scattering, gas transport, or later impacts. A partial barrier is less satisfying than a perfect one, but nature frequently avoids giving its mechanisms convenient settings like on and off. Jupiter may also have blocked entire planetary envelopes rather than known pebbles. As young cores formed beyond the snowline, interactions with the gas would generally cause them to migrate inward. Without an obstacle, several might have reached the inner edge of the disk and become hot super-Earths or sub-Neptunes. Gas giant opens a gap and creates a powerful gravitational barrier. In simulations, inward migrating super-Earths tend to collect outside the giant planet. They become trapped in resonances, collide, or scatter one another. Some are ejected from the system. A minority can cross the giant planet's orbit and continue inward. Jupiter and Saturn together make that passage more difficult. This led researchers to suggest that Jupiter may have prevented the growing cores of Saturn, Uranus, and Neptune from migrating into the inner solar system. Without an early Jupiter, whose bodies might have moved toward the Sun, becoming close orbiting super-Earths that our system lacks. This proposal is a different meaning to the question of whether Jupiter stole our super-Earth. Perhaps the missing planet was not supposed to form the Earth at all. Perhaps the bodies that would have become our super-Earths are still present, but they are now called Uranus and Neptune. Both planets contain roughly the amount of mass expected from large super-Earths or sub-Neptunes, although their thick, volatile, rich envelopes in distant orbits place them in the ice giant plateau. They may have grown from several smaller embryos that migrated inward through the outer disk and became trapped by Jupiter and Saturn. Simulations of ice giant formation explore this possibility. The population of planetary embryos beyond the gas giants migrates inward, but Jupiter and Saturn prevent the embryos from entering the solar system. The trapped bodies collide, allowing two surviving ice giants to grow. that model, Jupiter does not remove each planet. It changes when the planetary cores accumulate and what they eventually become. Without the power, those same cores want to continue upward. Their final atmospheres will be dependent on the available gas and the radiation they later received. Some could have become close in second channels. Others might have lost their atmospheres and appeared as rocky super-Earths. The solar system would then have looked much more ordinary from the perspective of Kepler's planetary census, and much less ordinary to anyone currently occupying Earth. Blocking pebbles and blocking embryos are related ideas, but they are not identical. Jupiter might have done both. Its core could first have reduced the liquid flow of solids. As it gained gas and became a giant planet, it could then have stopped larger and greater bodies. The sequence would need to occur in the correct order. The core must form early, must grow large enough to influence the disk before the other embryos would have acid. It must later collect the gas without migrating all the way to the sun. That last requirement is important because giant planets migrate too. Below Jupiter, embedded in the gas gids, we generally move inward, and the exoplanet systems contain hot, warm Jupiters, but they move much closer to their stars than Jupiter did. If our Jupiter followed the same path without interruption, it might have passed through the terrestrial region or remained close to the Sun. Saturn may have prevented that outcome. In the Grand Tech model, Jupiter formed first and began migrating inward. Saturn formed farther out and also moved toward the Sun. Because Saturn was less massive, its migration would be faster, allowing it to catch Jupiter. The two planets became locked in resonance. A combined interaction with the gas changed the planets' forces, reversing their direction and sending them outward together. The name comes from sailing. A boat changes direction by tacking. Jupiter's path in the model contains a similar turn. Jupiter moves inward, reaches a minimum distance, then moves outward after Saturn catches it. In the original version, Jupiter may have travelled inward to roughly 1.5 astronomical units, in the current orbit of Mars before reversing. The exact turning point remains debated and depends on disk conditions, gas accretion rates, and the masses of Jupiter and Saturn. The important feature is the large excursion, not one perfectly established distance. Such a journey would have made Jupiter less of a stationary guardian and more of a construction vehicle moving through the building site while the concrete was still wet. As Jupiter migrated inward, it would have scattered some planetesimals and pushed others ahead of it through resonances. The region available for terrestrial planet formation would have been narrowed to a band ending at Earth's present orbit. When Jupiter reversed direction, it would have removed and redistributed additional material. This translation offers an explanation for the small mass of Mars. Traditional simulations that give it a swiftly distributed disk often build a Mars far larger than the real planet. If Jupiter cleared much of the material beyond about 1 astronomical unit, Mars would go near the depleted anchorage and remain small. The same process would happen when an extra planet. Jupiter's movement would remove most of the original material, but would populate the region with complex scattering from both the Earth and the solar system. This offers a way to reduce the Earth's low total mass and varied composition. The Grand Tech was not invented mainly to explain the absence of super-Earths. It was developed to address the terrestrial planets in history belt. Once the abundance of closer exoplanets became clear, researchers realized that Jupiter's migration might also explain why the region is happening. proposed extension begins with an early generation of planets close to the Sun. These could have been super-Earths, smaller bodies moving towards super-Earth mass. When Jupiter migrated inward, it trapped swarms of planet descendants in resonances and sighted their orbits. Collisions ground much of the material into smaller fragments. Gas drive then carried those fragments inward. As the debris moved toward the Sun, it would interact gravitationally with pre-existing planets. Collective effect might cause those planets to lose orbital energy and fall into the Sun. Afterward, Mercury, Venus, Earth, and Mars would form from the reduced material left behind. This is the closest major model comes to saying Jupiter destroyed our super-Earths. It is also one of the more speculative parts of the story. There is no direct evidence that several large planets once orbited inside Mercury. We have not found the remains of what could be the New Zealand planet. The model demonstrates that such a theory is dynamically possible under certain assumptions. It does not prove the Big Bang. The original planets were beautiful and early, before Jupiter's migration. Jupiter and Saturn were horizontal close to the galactic path. Collision of the debris units interact efficiently with the planets. Finally, they to produce them four terrestrial planets with acceptable masses and orbits. Each step can occur in simulations, combining every step into one unavoidable mystery of orbit. There are also alternative models that explain the small mass of Mars and the limited terrestrial disk without requiring Jupiter to move as close as 1.5 astronomical units. Some models begin with a naturally narrow concentration of solids in the Earth's orbit. Others use an early instability among giant planets to disturb and repeat Mars-rim region. This pressure structures may concentrate material into rings before terrestrial planets form. Jupiter remains important in many of these models, its exact joint changes. Maybe a moving sculpture of one, a stationary barrier in another, or a source of later instability in the third. The phrase Jupiter stole our super-Earth is therefore useful only as a question, not as a conclusion. A finished super-Earth may never have existed. Jupiter could have starved the region before one formed. The life cores may have been stranded outside Jupiter and become ice giants. An early population may have formed and then fallen into the Sun. Several of these effects would have occurred together. There is another way to test the idea. If Jupiter-like planets become close to super-Earths, exoplanet surveys should find relatively few systems containing both. Early migration barrier models make exactly that prediction. Distant giant planets should block the movement and cores. Systems with cold Jupiter should therefore be less likely to contain compact groups of super-Earths. Observations have not produced a single answer. Several studies found that outer giant planets were at least as common, and possibly more common, around stars with bigger super-Earth than around comparable stars without. One analysis estimated that cold Jupiters appear more frequently in known super-Earth systems, while another radial velocity survey also reported an excess of Jupiter analogues among stars visible from small planets. Later, a cold survey of 38 Kappa and Q2 small planet systems found no significant excess of cold Jupiters, and it also did not establish the strong anti-correlation predicted by the simplest barrier models. The sample was not large enough to settle the matter. Larger recent analyses continue to find the relationship depends on whether planets and stars are selected. Stellar meteoricity of this group is disks rich in heavy elements and may be efficient at forming both in small planets and outer giants. A 2025 analysis using a larger sample found the overall cold Jupiter rate in small planet systems to be consistent with the comparison population, while allowing a possible positive connection to massive metal-rich stars. This does not eliminate Jupiter's role in the solar system. It shows that the presence of an outer giant is not enough by itself. The giant that forms late cannot stop everyone to the really migrated inward. A giant that forms far from the star may leave the disk unaffected. smaller giant may not create the same barrier. Gas can carry material through gaps. Super-Earths may form locally from solids that arrive before the giant became massive. Some planets can scatter past the barrier. The system may also contain enough material to build both populations. The architecture depends on timing, location, disk mass, intensity, vibration speed, and the growth order of the planets. Jupiter may have prevented super-Earths here and there. Every Jupiter-like planet being the same elsewhere. That makes the solar system's history more specific. Jupiter may have been the first major core in the correct region. It may have reached pebble isolation early enough to reduce the supply. It may have gained gas quickly enough to block the woody plates and embryos. Saturn may have formed at the correct time to stop Jupiter's onward journey. The later instability may be gentle enough to avoid destroying Earth units. Choose any one of those events, the result could be different. The slower growth of Jupiter might allow several embryos to pass inward before becoming a barrier. The inner solar system could require multiple super-Earths. Jupiter that migrated farther inward and stayed there might become affected by warm Jupiter, perhaps disrupting the terrestrial planets. A system without Saturn might fail to reverse Jupiter's migration. The weaker pebble barrier might allow Earth to continue growing, producing a planet several times its current mass. More violent encounter among the giant planets would eject one of them or destabilize the rocky worlds. The familiar solar system may therefore depend less on Jupiter simply being present than on Jupiter doing several things at particular times. Is that likely? Possibly, although not with the usual comet of gravity sense. It may have guarded the inner system from excess mass. Was it a bully? Perhaps. Its vibrational resonances could have scattered planetesimals, completed the disk, and removed an earlier generation of planets. Was it a cosmic bouncer? That may be the best of the three descriptions. The growing Jupiter could have stood between the outer supply and the inner system, rocking pebbles and turning back migrating embryos. There are few objects and plenty of small material still slipping past. Did it steal our super-Earth? There is no evidence that Jupiter quietly took one planet and mixed it somewhere else. More plausible claims that it changed the conditions so thoroughly that the closest super-Earth had never formed somewhere else, it did not survive. Jupiter may be the reason Earth is removed rather than Earth remains. It is an extraordinary possibility because it means our planet's size was partly determined by an object that millions of kilometers away. The effect would not have required Jupiter to approach Earth directly. Controlling the movement of material through the disk could shape planets at great distances. The amount of rock in the terrestrial region, the timing of embryo growth, and the migration of outer cores would really depend on Jupiter's early development. Even then, Jupiter cannot explain every detail of the name. Mercury's unusually large iron core, the exact masses of Venus and Earth, the formation of the Moon, the delivery of water, and the present asteroid belt require additional events. Saturn's role is substantial. Ice giants probably would. The giant planets later experienced instability. Gas disks contain structures that remain poorly known. A single cockpit is convenient. The planetary system is built on a sequence. The evidence allows us to say that Jupiter formed early enough to matter. Theory shows that a growing giant can block pebbles and migrating cores. Migration models demonstrate that Jupiter could reshape the terrestrial disk or help to remove an earlier in the population. Exoplanet observations warn us that outer giants and the super-Earths can coexist, so Jupiter's presence alone is not a universal explanation. What remains uncertain is whether our solar system ever crossed the line from ingredients with super-Earths to actually having the planets themselves. A barrier that prevented their birth, and a clearing event that destroyed them, that produced the same present-day result. An empty region inside Mercury with no path between Earth and Neptune. To separate those possibilities, we have to ask what evidence of action planet might be behind. That sounds straightforward until we consider the number of ways a planet can vanish. It can collide with another planet and become part of it. It can break into debris scattered across the system, and spiral into the sun, and thrown into a distant orbit, or ejected completely into interstellar space. After more than 4.5 billion years, each route will leave a different collection of clues, and some might leave very little that can recognize fragments. At present, there is no direct evidence that a complete system of super-Earths once orbited close to the Sun, and no surviving moon can be confidently identified to Captain 1. No meteorite that comes with a return address through the former in the super-Earth. No gap on the known planets that requires a missing body of several Earth masses. The idea comes from computer models that try to explain why our system differs from common planetary systems found on the stars. One influential model shows how early planets could have been removed, but other successful models begin without them. The most direct lost super-Earth scenario is connected to Jupiter's proposed configuration. In this version of the young solar system, solid bodies have already formed inside the region now occupied by Mercury. Some will have grown into short-period planets, possibly including super-Earths. Jupiter then migrated inward through the galaxies, reaching much closer to the Sun than its present orbit before Saturn had to reverse its direction. Jupiter would not have needed to collide with other planets. Its resonances would have pushed large numbers of planetesimals onto crossing orbits. Repeated collisions among those bodies would have produced a cascade of fragments, gas cloud, and then caused much of the debris to drift toward the Sun. As the inward-moving material interacted gravitationally with any existing planets, it could remove orbital energy from them. Planets would gradually move closer to the Sun until they were swallowed. Simulations published by Constantine Montague and Gregory Lafford demonstrated that this process could clear short-period planets by leaving behind a depleted reservoir in which Mercury, Venus, Earth, and Mars later formed. It is an elegant idea that in several unusual features of the solar system, the region inside Earth is empty. Terrestrial planets contain much less mass than the compact systems detected by Kepler. Mars is small. Jupiter is far from the Sun despite the tendency of giant planets to migrate. One event involving Jupiter could contribute to all of these outcomes. Elegance, however, is not the same as evidence. The simulation shows that early planets can be removed under the required conditions. It does not show that those planets definitely existed. Calculation begins with an assumed inner population and explores what Jupiter's migration would do to it. If the assumed planets are destroyed, the result demonstrates a possible route, not a common history. This distinction matters whenever scientists use simulations to reconstruct events that cannot be watched directly. Computer model begins with selected masses, positions, disk conditions, and rules for collisions and gas cloud. Researchers then test whether the system evolves into something resembling the present solar system. The successful result tells us that the proposed history is physically plausible. It does not tell us that nature chose that history from every available option. There is also a timing problem. The super-Earths would need to form before Jupiter completed its inward journey. Building planets of several Earth masses requires a large supply of solids and efficient growth. If Jupiter's core formed early enough to block the inward flow of planets, the inner disk may never have received enough material to build those planets in the first place. The same Jupiter cannot easily be invoked as both an early planet that prevented rapid inward and a later destroyer and fully developed super-Earth system, unless the timing allows for its stages. Perhaps substantial material entered the disk before the barren formed. Perhaps small planets grew quickly from events in the ring. Perhaps Jupiter became effective only after the first generation was established. Each addition can make the scenario work, and each also introduces another condition that must have occurred in the correct order. For this reason, some researchers argue that the solar system probably never contained a compact system of close and super-Earths. In their preferred picture, Jupiter formed early and prevented outer planetary embryos from migrating toward the Sun. The cores that might have become close orbiting super-Earths remained beyond Jupiter, and contributed instead to Uranus and Neptune. The inner disk was left with too little mass to build planets much larger than Earth. That explanation requires no vanishing planetary boundary. The missing worlds were prevented rather than removed. A different group of models reduces Jupiter's role even further. These begin with the solid material of the young solar system concentrated into several rings. Pressure bumps in the gas disk trap in dust patterns at particular locations. Planetesimals form inside those concentrations instead of being distributed smoothly from the Sun to the outer planets. In one detailed ring model, a thin band of rocky material supplies Mercury, Venus, Earth, and Mars. The second ring near the water snow line helps build the cores of the giant planets, while an outer ring contributes to more distant populations. Simulations show that this arrangement can reproduce several features of the solar system, including the division between inner and outer material according to the meteorites. Terrestrial planets remain relatively small because the rocky ring contains a limited mass. There is no need to form several super-Earths and dispose of them afterward. The amount of material trapped in such a ring will determine the kind of planetary system that develops. A massive silicate-rich ring can produce several rocky super-Earths. A lighter ring can produce smaller planets resembling those around the Sun. Recent modelling of rocky super-Earth formation showed that the same broad mechanism can yield very different systems depending on how much solid material the ring collects. This gives the young solar system a less dramatic history. Nothing large needs to fall into the Sun. The disk simply begins with the distribution of material that favours four modest rocky planets instead of a compact group of heavier ones. I also explain how the emptiness inside Mercury is so complete. Planetesimals formed mainly in a ring centered farther out. The innermost disk could contain dust and gas without producing many large solid bodies. Lucky planets close to the Sun will be future collision constructions of not horizontal related here and there. Mercury might appear to challenge that idea because it does exist at the edge. It has a neutral composition. About 70% of its mass is associated with its metal-rich core, far more than the approximate proportion found on Earth. One proposed explanation is that Mercury began with a larger rocky mantle and lost much of it in a giant collision. Models have shown that debris from such an impact might be removed by the strong wind of the young Sun before it fell back into the planet. It is tempting to wonder whether Mercury is the strict remains of the super-Earth. Numbers may not unlikely. Mercury has only about 5.5% of Earth's mass. Even if we use a simplified calculation which its present measurable mass represented 30% of a more Earth-like planet, the original body had only around 30% of Earth's mass. The precise value depends on the suit composition and how much material is removed. But restoring a missing mantle does not turn Mercury into a world several times more massive than Earth. Mercury may be the survivor of a small collision, an unusual chemical environment in the Sun, with several related processes. It is not a given 5 Earth mass planet or a very small rocky project. It even some Earth contain more mass. Neither provides clear evidence of the assemblage of organisms in the super-Earth. Their growth involved many embryos and major impacts, as expected in terrestrial planet formation. Earth's moon probably formed after one such collision. This shows that large bodies disappeared as separate objects by becoming parts of the surviving planets. But those impactors were planetary embryos rather than the third lost generation of close super-Earths. The planet does not material as a corpse. If an object collides with Earth, its core may merge with Earth's core, and its mantle mixes with a mantle, or its part eject. Chemical and isotopic differences can sometimes preserve information about second source regions, but billions of years of melting, differentiation, mantle circulation, erosion, and later impacts make it difficult to reconstruct every regional body. Bayer, a critical impact involved in root formation, is a good example. Scientists can model the collision and examine the compositions of Earth and the Moon, yet the impactor's exact mass, composition, and origin remain debated. Reconstructing one major collision is difficult, identified several planets that vanished earlier in hot gas-filled disks considerably harder. Meteorites provide older and less processed evidence, and mostly sample displays and fragments of small differentiated bodies. Isotopic compositions reveal that the inner and outer solar system contain distinct reservoirs of material. A not constrained image would have been disk pressure barriers today. We do not show that several Earth-class planets occupy the region in some way. Some meteorite evidence has been used to support both the growing Jupiter area and an earlier pressure band in the disk, which illustrates how one observation can be often with one physical explanation. The asteroid belt is another possible place to search for anomalies. Today, its total mass is very small, however, for the terrestrial planet. It cannot be the intact rubble of several super-Earths, unless almost all of the original material is removed. That removal is possible with Jupiter. Resonances, collisions, and later instabilities heavily depleted the belt, but the surviving objects do not identify one specific lost planet. They show that the region experienced extensive mixing and depletion. Bodies from different parts of the disk were placed together, when others were scattered, colliding with planets, fell into the sun, or escaped. The belt is a collection of supernovas, not merely a storage shelf. The sun itself contains matter. Stars can swallow planets. When rocky material enters a star's outer layers, it can alter the abundance of elements that condense at high temperatures. Astronomers have found chemical differences between stars all together that are consistent with one member of just planetary material. The 2024 study of comingled stellar pairs identified evidence of planetary gesture in 7 cases among the 91 pairs included in its main analysis, showing that engulfment is not merely a theoretical possibility. The sun is hard to tell, as it does not have a confirmed stellar twin with exactly the same material inside it. Its present composition can be compared with similar stars. Differences may arise from the chemical evolution of the galaxy, the sun's birthplace, or its formation, inclusion inside the star, or ingestion. The 2026 analysis of solar twins found that much of the sun's chemical peculiarity could be explained by galactic chemical evolution, rather than by a clear record of swallowed planets. That work does not prove the sun of nothing. It shows how difficult it is to turn stellar abundances into a reliable list of missing worlds. Time creates non-communication. The young sun are much thicker convected out of air than it has now. The rocky material swallowed earlier would be diluted through a large amount of stellar gas. Chemical signal from several planets would become weak or ambiguous. By the time the sun's outer mixing air became shallower and easier to read measurable, the main gas-filled migration period was already over. The sun could therefore consume planets without preserving the surface level. Chemical chemical signature does not rule out engulfment. Neither does the general fact that other stars consume planets establish that our sun consumes super-Earths. Another possible destination is interstellar space. Gravitational encounters can eject planets, especially in systems containing multiple giant planets. A super-Earth scattered by Jupiter might receive enough energy to escape the sun entirely. Once gone, it would leave no objects nearby to examine. Inflated planets discovered elsewhere in the galaxy show that planetary ejection occurs, although their original systems are usually unknown. Ejecting a low-mass planet from the solar system is not as simple as imagining it out at once. It would generally need a sequence of encounters that carried across the orbits of large planets. Those encounters would also disturb Jupiter, Saturn, the terrestrial planets, and the small body populations. A successful history must remove the planet while preserving the architecture we see. The early solar system probably did eject at least one major body, but the strongest versions of that idea involve an additional ice giant rather than a closely super. Models of the giant planet instability often begin with 5 giant planets. Jupiter has a close encounter with the extra planet and throws it out of the system, while 4 known giants survive. planet's body would have been more similar to Uranus or Neptune than to a little super-Earth with the Sun. This demonstrates that a planet can vanish without leaving easily identified elements. It does not establish that same thing in the terrestrial region. Giant planet instability may shape the solar system in another way. If it occurred while the terrestrial planets were still growing, resonances associated with Jupiter and Saturn will move material from the Mars-forming region and the asteroid belt. Numerical experiments show that an early instability can help you pass small while allowing Earth and Venus to go closer to the Sun. This model begins with embryos and planetesimals rather than a complete system of super-Earths. The instability depicts selected regions before the other planets finish assembling. Once again, the solar system's low mass can be explained by interrupting growth instead of destroying finished planets. Many alternatives can therefore be placed into two new planets. In one family, the young solar system began with enough material to be closer to planets larger than Earth. Those waves formed early, then migration, debris, collisions with the Sun and the Moon. The present terrestrial planets formed after from in the other family, the super-Earths never formed. It is concentrated solids into a limited working world. Jupiter blocked the incoming supply, or an early instability removed material that was still divided among embryos and planetesimals. Earth is the largest surviving rocky planet because the construction materials ran out before everything became much larger. Both families can reproduce important features. Neither explains every constraint perfectly. The lost planet model offers a direct reason for the empty region inside Mercury. It uses processes known to occur in other systems, including operational star involvement. Its weakness is that it requires an unseen first generation, a specific version of Jupiter's migration. Prevention models require fewer vanished planets and are supported by the ring structures observed in many protoplanetary disks. Their weakness is that the exact structure of the Sun's disk is unknown, and several different combinations of rings, pressure bumps, giant planet growth, instability produce similar final results. Scientists try to separate these possibilities among their predictions. A model should reproduce the masses and orbits of Mercury, Venus, Earth, and Mars. It should account for the small mass and mixed composition of the asteroid belt. It should agree meteor ages and subsequent reservoirs. It should allow Jupiter, Saturn, Uranus, and Neptune to reach their present arrangement. It should deliver the appropriate quantities of water and volatile gas to Earth. It should also work on simulations that the solar system does not require every collision and migration step to be adjusted by hand. This is a demanding list. The model that explains Mars may struggle with Mercury. The model that creates the correct asteroid belt will dilute too much water. The model that places Jupiter correctly may not go too quickly or too slowly. The young solar system may many attractive planets, improving one result of the disturbed model. Future evidence may come from better measurements of Mercury, Venus, asteroids, comets, and the Sun. Samples returned from 20 selected small bodies and test what different materials formed. More precise planetary interior measurements may constrain collisions which were experienced. Observations of young planetary systems can show that super-Earths usually appear before giant planets, where the giant cores block their migration, and more often the planets fall into their stars. Exoplanet surveys may provide another useful comparison. If systems with early distant Jupiters consistently lack closer to super-Earths, barrier explanation gains support. If two populations commonly coexist, Jupiter alone cannot be responsible. Current observations already show that less small planets and intergiants occupy the same system, which means timing and disk structure matter at least as much as the presence of a giant planet. The fairest answer is that our solar system may once have contained super-Earths, but we do not know that it did. Complete inoculation of the fallen into the Sun. The mechanism is physically plausible and has been demonstrated in simulations. It remains an assumption, likely, An observed stage by history, with plausible bodies for the terrestrial planets in a restricted supply and never create missing worlds. The absence of evidence is especially difficult to interpret when a proposed event is designed to remove the evidence. Planets swallowed by the young sun cannot be photographed now. Planet ground into dust and mixed among later worlds will not immediately identifiable. Yet a mechanism, though hard to disprove, does not make it a preferred explanation. For the moment, the safer conclusion is that the solar system's unusual architecture was established very early. Either it failed to build common closing planets, or it removed them before Earth completed its growth. In both cases, the important events involve the distribution of solid material, the timing of Jupiter, the movement of planets through gas, and the instability that followed. That combination gives the solar system an architecture that was not impossible, and appears uncommon among the planetary systems we currently detect. We have several small rocky planets close to the Sun, no planets on extremely short orbits, no super-Earths with sub-Neptunes, low mass asteroid belts, two gas giants with wide, nearly circular paths, two smaller ice giants farther out, and a broad population of icy objects beyond Neptune, which feature to be explained individually. Finding all of them together is where the difficulty begins. Before exoplanets were discovered, this arrangement seemed like a reasonable model for planetary systems in general. The warmer region near a star produced rocky planets because only heat-resistant materials grew on the solid bed. The colder outer region provided ice as well as rock, allowing planetary cores to grow quickly and capture large quantities of gas. Small planets belonged to the star. Giants belonged to the fairy realm. The solar system appeared to demonstrate the basic rules. Thousands of exoplanet discoveries showed that those rules describe possibilities rather than fixed instructions. NASA's confirmed exoplanet count reached 6,000 in 2026, and the known population includes hot Jupiters, compact groups of super-Earths, sub-Neptunes, planets orbiting two stars, and systems whose entire known planetary family fit inside their orbit. Our arrangement is only one result of another. The first unusual feature is the emptiness close to the Sun.
Immediately raise some care with superior sun protection. Premier sun protection question.
I remember finding this one. Background removers for little. This is for the distance. You can see from that, honey, I don't
Like anything, right, honey?
Mercury is the nearest planet, but its average distance from the Sun is about 58 billion kilometers. Its year lasts 88 Earth days. That sounds close until you compare it with exoplanet systems containing planets that compute in orbit in 10 days, 3 days, or less than 1 day. Many known systems have several planets inside the equivalent of Mercury's orbit. These worlds are not distributed randomly. They often form closely packed groups with neighboring planets separated by modest distances. Some are near orbital resonances, which suggests that they migrated through a gas mask and settled into their present arrangement. The solar system has enough room inside Mercury's orbit for several of these planetary paths, yet the region contains no known planet. There may be small asteroids close to the Sun, and hypothetical populations such as Vulcanoids have been proposed. Searches have not revealed a substantial hidden planet. The world, even roughly the size of Earth in that region, produced noticeable gravitational or gravitational effects. This inactiveness is not merely a consequence of Mercury being small. It reflects a lack of planets across a wide range of extraterrestrial periods. We have no ultra-short period Rocky world, no hot super Earth, no warm sun action. The absence could mean the young solar system never concentrated enough solid material close to the Sun. could mean an early population migrated into the sun. It could also reflect the movement of the disks of an age. Each possibility changes the story. The present result is the same. Our planetary family begins unusually far from the star compared with many systems from through transit surveys. Some of the apparent contrast comes from detection lines. Short period planets are easier to discover. They transit more often, have a higher chance of crossing their stars from the orbit, create stronger gravitational signals than the massive planets on wide orbits. A telescope designed to find transits will actually collect systems close to their stars. Our current material therefore exaggerates the prominence of compact systems. Distant solar system-like planets require longer observation periods and more sensitive instruments. A Jupiter hangout takes nearly 12 years to complete one orbit, while a Neptune hangout takes about 165 years. Further hangout undermines a substantial portion of an astronomer's career, which is a rather severe method of encouraging professional commitment. The bias does not make compact systems imaginary. Statistical corrections still show that close-in super-Earths and sub-Neptunes are common. Simply means we should not compare all network detected compact systems with the solar system, but conclude that almost every star looks unlike the Sun. The true frequency of systems like ours remains uncertain, because the planets that define our architecture are among the hardest to find. Even with that caution, innocent planets between Earth and Neptune remain striking. Super-Earths and mini-Neptunes are common among known exoplanets, while our system contains no equivalent. NASA describes super-Earths as a class of anything in the solar system, with possible compositions ranging from rock to gas-rich mixtures, and notes that these worlds are common among the planets discovered so far. Earth is the largest terrestrial planet, with only slightly more mass than Venus. Neptune is more than 17 times Earth's mass. There is nothing between them. That gap may be telling us that the inner planets stopped growing unusually early. Earth and Venus collected enough material to become large rocky worlds, but not enough to develop into them that would cause commonly seen elsewhere. Mars remained much smaller, and Mercury contains only a fraction of Earth's mass. The 2018 review of the solar system formation of exoplanet systems argued that our architecture may be unusual at approximately the 1% level among sun-like stars, although the estimate depends strongly on how the solar system is defined within the spectrum of surveys. The same review emphasized that the system may be the outcome of several uncommon events rather than one extraordinary event. That distinction is important. A person who rolls 4 dice and receives 4 sixes is not witnessed an industrial event. Each die behaving normally. The unusual part is the combination. The solar system may be similar. Jupiter formed through ordinary physical processes, Saturn formed through ordinary physical processes. Rocky planets grew through collisions. Migration and instability occurred. None of those events needs new physics. The rarity may come from their order, timing, and severity. Jupiter's core may have formed early enough to limit the big flow of planets. Interplanetary embryos may then have been too small to migrate far through the gas. Saturn may have formed at the right time to influence Jupiter's movement, prevent it from becoming a hot Jupiter. The later instability among the giant planets may have been strong enough to rearrange them, but not strong enough to remove Jupiter, Saturn, Earth, or Venus. Many systems probably fail at those points. Giant planets may migrate inward and become a hot Jupiter. Its movement can disturb or remove smaller inner planets. A system of super-Earths may form before into large enough to block them. Several giant planets may scatter one another onto eccentric orbits. One may be ejected, another may be close to the star. Inner planets may collide or be thrown away during the disturbance. A giant planet has comparatively low orbital eccentricities. Their paths are not perfect circles, but they are far less stretched than those of many giant exoplanets. This suggests that the solar system's giant planet instability, if it occurs, current models propose, may be without the most destructive possible encounters between Jupiter and Saturn. The 2018 review identified this comparatively gentle outcome is one of the events that will distinguish our system from many giant planet systems. The violent encounter between Jupiter and Saturn it changed much more than their own orbits. Their gravitational fields would spread into terrestrial region. Earth and Venus could be left on more eccentric planets, alive or be ejected. Asteroids and comets would be scattered widely. Present stability of the system faces limits from how chaotic the giant planets pass through being. Neptune and Uranus have another unusual feature. Their masses are similar enough for both to be called ice giants, but their positions and internal structures are not easy to reproduce in formation simulations. Their present distance as the disk may contain too little solid material or cause to grow quickly before the gas disappears. Many models therefore place their formation closer to the Sun, followed by an outward movement during the giant comet's instability. There are also been survivors of a larger original group. Some simulations begin with an additional ice giant as an interjected by Jupiter. Losing one large planet but remaining four giant groups that can orbit. If that happened, the solar system's present kind of electrons might seem similar, although the missing object would probably have resembled the Earth's or actually more than a rocky super. The outer planets also have a large amount of orbital space between them and very compact systems. Their space contributes to long-term stability. The type of chain of the large planets is more vulnerable to gravitational disruption, especially after the gas disappears. And giants occupy broad separated paths, giving them less opportunity to encounter one another closely. This does not mean the system's perfectly fixed. Planetary orbits change slowly under neutral gravitational influence. Small bodies are scattered. Comets move inward. Some asteroids enter resonances. The system's dynamic, its major planets have remained stable for billions of years. The inner planets are also more widely separated from those of many planet systems. Astronomers studying compact multi-planet systems have noticed that neighboring planets often have similar sizes. This tendency is sometimes described informally as peas in a pod. The system may contain several planets, that are all roughly Earth-sized, or several that are all in the same action average. The planets aren't identical, but their sizes and regular spacing suggest that they group in related conditions that influence one another during migration. The solar system does not fit that pattern particularly well. Mercury, Venus, Earth, and Mars differ greatly in mass. Earth is more than 18 times as massive as Mercury, and about 9 times as massive as Mars. The jump from Earth to Jupiter is enormous. Saturn is much less massive than Jupiter, and Uranus and Neptune fall in a smaller pair. One recent theoretical study proposed that systems of super-Earths may develop their relatively uniform masses through repeated formation at pressure bumps created by other planets. In that model, worlds near the pebble isolation mass encourage the formation of additional similar planets, producing chains of comparable super-Earths. Smaller Earth-like planets that can never reach pebble isolation but have more varied masses, closer to the uneven terrestrial family found around the Sun. That proposal remains one developing explanation that illustrates a useful point. Earth may not be a slightly undergrown network of super-Earth population. Earth-sized planets and super-Earth systems may sometimes hold meaningfully different growth patterns. The amount of available solid material can create this division. A massive inner disk may build several cores until each reaches a similar limit in mass. A less massive or interrupted disk can produce a handful of smaller bodies with less regular sizes. Our terrestrial planets could be the outcome of the second process.
To some extent, there have been developed with dermatologists, science, certified by British Foundation.
Yeah, you could say, throw Excel, trade in your phone, play next to two, you can't cash that. Plus,
asteroid belt reinforces the impression of limited material. The total mass of the belt is far smaller than the mass of Earth. It is not the remains of a destroyed Earth-sized planet, despite a common popular idea. Its objects occupy a region where a planet might seem able to form. Jupiter's resonances, the growth of the terrestrial planets, and later instabilities prevented the material from collecting into one large world. The belt's small mass and mixture of compositions suggests that most of its original material was removed, and that surviving objects come from different parts of the Earth. The success of a solar system model must explain why the belt exists, why it is so depleted, and why it contains both relatively dry and volatile rich bodies. Compact exoplanet systems often do not have an obvious equivalent. This does not prove they lack asteroid belts. Small belts are extremely difficult to detect from distant stars. Dusty debris disks can be observed in some systems, but a mature belt with as little material as ours can remain invisible. This is a recurring problem when judging whether the solar system is unusual. We know our own system in reasonable detail. We have landed on planets and moons, returned asteroid samples, measured meteorites in laboratories, and monitored planetary motion for centuries, and sent spacecraft to bring Neptune. Most exoplanet systems are represented by a few measurements of starlight. Comparing the two is like comparing a complete fundamental history with silhouettes seen through a film. The distant observer using methods similar to ours might fail to detect most solar system planets. Earth produces a weak radial velocity signal in transit only if the observer occupied in the whole line of sight. Jupiter is easier to detect. Confirming its long orbit would require many years. Saturn's signal is weaker and slower. Uranus and Neptune will be harder still. The 2018 formation review noted that, with the detection technology available at the time, Jupiter might have been the only solar system which regularly detectable from another star. Such an observer can classify the Sun as a star with one cold giant and an unaware of the rest of planets, Saturn, the ice giants, the asteroid belt, and nearly everything else that defines the system. Detection technology has improved since then. The underlying problem remains. We do not yet have complete senses of true solar system worlds. Some systems initially described as similar turn out to be different when examined closely. Kepler 90 contains 8 known planets and has small worlds inside large ones, which resembles the broad order of our planets. Yet all 8 Kepler 90 planets orbit with a roughly Earth's orbital distance. This is an extremely compact system, and its other planets are too hot to close over equivalents. Other systems contain a Jupiter planet on a wide orbit with no detected Earth. That may mean there is no rocky planet, or it may mean the rocky planet is too small to detect. Some contain almost super-Earths, as well as anti-giants, demonstrating that a cold Jupiter does not always prevent close planets from forming. Research into the relationship between inner super-Earths and anti-giants has produced mixed results. One influential study found that cold Jupiters occur more frequently than stars already named post-super-Earths, and concluded that solar system-like systems with cold Jupiter, but no inner super-Earths should be rare. Later surveys have not always found the same structural correlation. Samples remain limited because detecting both populations in one system requires combining short-period planet searches with observations lasting many years. Stellar meteoricity, selection effects, and the precise definitions of super-Earth and cold Jupiter can all change the result. What can safely be said is that outer giants and inner super-Earths are capable of forming together. Jupiter's existence alone does not guarantee a meteor region. Timing and location of its formation does matter. The Sun itself is fairly in some ways. It is a middle-aged, hydrogen-burning star of a common general type. Although stars smaller and cooler than the Sun are much more numerous in the galaxy. Its chemical composition is not extreme, and it is not part of a close boundary system. That last feature may have helped the planets remain relatively orderly, and stars have stellar companions. The nearby companion can truncate the planet-forming disk, disturb planetary orbits, influence the delivery of comets. Stable planetary systems can still foreground one or both stars, with available architecture dependent on the Some may also have fallen in a stellar cluster, as most stars probably do, then drifted away from its siblings. Close encounters during the cluster phase could have affected the outer solar system, although there is no agreed reconstruction of the sun's original model. When an encounter strong enough to alter Neptune and the Kuiper belt, it would occur without severely disturbing the planets. Another unusual feature may be the balance between movement and survival. The solar system was active enough to mix materials and deliver water-bearing bodies toward Earth. It was not so active, and Earth was moved close to the sun and thrown out. Jupiter altered the disk without forming a terrestrial region. Giant planets shifted without destroying the rocky planets. Large impacts occurred, including the event associated with the moon's formation, but Earth remained in a suitable orbit afterward. This balance can look good fun and be fortunate, although we must be careful about interpreting it. We observe the solar system from a planet whose history allowed observers to evolve, and the different architecture had removed Earth, placed it near the sun, or left it without long-term surface water, no longer be able to carry out the design. This creates a selection effect. We should not be surprised to find ourselves in a system compatible with our existence, even if such systems are uncommon. That reasoning does not explain how the system formed. It only warns us not to confuse compatibility with Earth's. Jupiter did not form in order to protect Earth, and the Moon did not form in order to stabilize everything. The solar system did not arrange its planets with huge biology in mind. Physical events produced many outcomes, and life appeared in the hands of one outcome when conditions were suitable. It is also possible that systems unlike ours are equally capable of supporting life. A compact system can contain a temperate-looking planet, especially around a small, cool star. A system with super-Earths will provide stable planets with long-lived atmospheres. A planet larger than Earth might remain geologically active for longer. A system without a Jupiter could avoid some disturbances while still delivering water through the roots. Our system is the only known example of the life. One example is not enough to identify which architectural features are necessary and can merely historical details. The absence of a close and square may affect Earth remaining in its current orbit. Several Earth mass planets nearby will disturb Earth's eccentricity, alter influence, change the delivery of water. One can also exist peacefully, depending on its exact orbit and the arrangement of the other planets. There is no universal rule that a super-Earth would make an Earth-like planet impossible. No multi-planet system shows that several closely spaced worlds can remain stable for billions of years. Resonances and regular spacing preserve order even when the system looks crowded by our standards. Likewise, Jupiter's presence may have influenced Earth's water supply over past history, but whether it increased or decreased habitability depends on which objects and time periods are considered. A simple picture of Jupiter as a shield has been replaced by a more complicated one, involving both removal and delivery. The solar system's unusual character is therefore architectural rather than obviously biological. It contains an uncommon combination of planet sizes, spacings, and orbital histories. It lacks the close-in worlds that dominate many exoplanet catalogues. It kept its largest planet far from the Sun. Its giant planets retained relatively calm orbits. Its terrestrial region received enough material to build Earth and Venus, but not enough to build several super-Earths. Its later instability did not erase the inner system. The result here required several events to occur in limited ranges. Jupiter had to grow early, but not migrate too far. Saturn had to influence Jupiter, but not destabilize it completely. The rocky planet had to grow slowly enough to avoid strong gas-driven migration, but quickly enough to form before the remaining material was removed. The giant planet instability had to rearrange the outer system without making Earth to orbit out. None of those events was individual, it was they produced a planetary family of hundreds of neutral systems comprehend. The word unusual should be done provisional. Future telescopes may discover many distant systems with small rocky planets, empty close-in regions, and cold giants on wide orbits. Current instruments are better at finding the systems least like ours and precisely the ways they activate. In comparison, requires detecting Earth-sized planets on year-long orbits, and Neptune-sized planets take more than a century to circle the stars. That work will continue for decades. As the census improves, the solar system will become less strange and turn out to represent a quiet, difficult-to-detect class. Alternatively, improved surveys will confirm that systems like ours are genuinely rare, and that most planetary disks produce compact super-Earths, migrating giants, or both. Either results will be important. Common solar system architecture will show that our present sample is shaped heavily by observational bias. The rare architecture retains the Earth's formation dependent on the narrow sequence of events. It will not make Earth the centre of the universe. It will make our route through planet formation less typical. Most interesting comparison on our route through the whole solar system and every known exoplanet system. It may be between Earth and worlds that formed where Earth did not. Rocky planets several times heavier, water-rich planets with deep oceans, and sub-Neptunes wrapped in thick atmospheres. Those planets occupy the missing part of our family. Being larger than Earth will either an advantage, a serious problem, or something in between, which is why the habitability of super-Earths cannot be determined from size alone. A planet may have the correct orbit, a stable climate, liquid water, and an atmosphere that protects its surface. Another planet with almost the same radius may be buried under hundreds of kilometers of gas, covered by molten rock, and exposed to radiation from a star. The first question is whether Earth has a surface at all. Dense super-Earth, mainly of iron and silver rock, should have a solid exterior, although that exterior might be hidden in oceans, ice, clouds, or lava. The low-density planets in the same broad-sized atmosphere don't have a thick hydrogen and helium envelope. As pressure increases deeper inside that atmosphere, the gas gradually becomes denser and hotter. There may be no clear boundary where a traveller would point down and say, there is the ground. This is why the distinction between a rocky super-Earth and sub-Neptune matters so much. A rocky world can potentially provide a surface where liquid water interacts with minerals, atmosphere, and sources of energy. The sub-Neptune can instead contain a deep gaseous envelope where layers of rock fluid and high-pressure material. Life could perhaps exist in an atmosphere or ocean under unfamiliar conditions. That possibility is much harder to evaluate because we have no practical environment in the solar system. Astronomers begin with mass and radius. Those values provide an average density, which helps narrow the possible compositions. A planet that is only 1.5 times Earth's radius and 6 times its mass is likely to contain a large amount of rocky matter. A world twice Earth's radius, only 3 times its mass in substantial low-density material. The answer is rarely a planet with a certain density might contain an iron core, a rocky mantle, and a moderate ocean. It might instead have less water and a light atmosphere. The interior bodies produce several arrangements that fit some measurements. Habitability therefore begins with an uncomfortable number of unknowns. We may know the planet's diameter to within a few cent and still be unsure of its continents. The next question is temperature, which leads to the habitable zone. This is the range of orbital distances where a rocky planet with a suitable atmosphere can maintain liquid water on the surface. It is a useful way to select targets, but it is not a certificate of practical conditions. A planet in the habitable zone could lack water, possess almost no atmosphere, or suffer an extreme greenhouse effect. NASA treats the habitable zone as an initial filter rather than proof of habitability, and emphasizes that planetary size, atmospheric properties, and the behavior of the host star is also considered. This provides a nearby warning planet lies close to the inner edge of the sun's broad habitable region in sunlit conditions. It is almost the same size as Earth. Its thick carbon dioxide atmosphere reduces surface temperatures to near low. Mars shows the opposite problem. It occupies a more distant orbit and has evidence of past surface water. Its atmosphere is now thin, and much of the planet is cooled and dry.
Skin getting dried out. Feels tingly from sonic skin or in shower gel. Once a month, for legal fees, less than me, everyone will pay. What do you think? It's not the big business. Sorry. So soon, like anything, I come in.
Moving a planet in correct distance does not require a work condition. A larger rocky planet may have several potential advantages. Stronger gravity helps it retain atmospheric gases. Its interior may remain hot for longer, as a large body cools more slowly than a small one. Continued internal heat can support volcanism, recycle gases, and maintain geological activity over billions of years. Mars lost much of its early geological activity partly because it is small. Its interior cooled relatively quickly, its global magnetic field weakened, and its atmosphere became vulnerable to erosion. Super-Earth avoids such problems. Greater mass does not guarantee an Earth lifetime, however. Stronger gravity can produce a much thicker atmosphere. The planet collects hydrogen and helium from the protoplanetary disk. They hold those gases far more successfully than Earth would. A small envelope mass with high surface pressure and strong greenhouse warming. A planet several times Earth's mass might also retain large amounts of carbon dioxide, water vapor, methane, or other gases released by volcanoes. Without an effective nature removal story, the atmosphere can become dense and hot. Earth's climate is influenced by a long-term carbon cycle. Carbon dioxide is released through volcans, removed from the atmosphere through reactions involving water and rock, carried into the planet by moving tectonic plates, and later returned through geological activity. This feedback helps regulate climate over long periods, although it has not prevented major climate changes. Whether super-Earths have plate tectonics is uncertain. Larger planets contain more internal energy, which could encourage mantle movement. But greater gravity also increases pressure and may strengthen or compress the outer shell in ways that make plate motion more difficult. Different models have reached different conclusions because tectonics depends on rock properties, water content, temperature, mantle circulation, and the history of the surface. The super-Earth might have active plates, a single unmoving lid, repeated episodes of resurfacing, or a style of geology unlike anything found on Earth. Studying the hot super-Earth GJ486b, for example, researchers modeled forms of atmospheric mantle circulation that could arise on a tightly locked world, demonstrating that the interior behavior of these planets may differ substantially from the familiar tectonic patterns of Earth. A magnetic field presents another uncertainty. Earth's field is generated by moving electrically conductive material through its liquid outer core. It redirects much of the charged particle flow from the sun and helps reduce direct erosion of the atmosphere. A massive rocky planet may have a large magnetic core. That does not automatically produce a strong magnetic field. The core must contain moving liquid, release heat in the correct way, and maintain convection. A planet with large enough for its interior to remain hot, while also having pressures that change how its core salute fans. Slow rotation may alter the shape and structure of the field. Magnetic fields are also difficult to detect around small exoplanets. Astronomers can model what might happen, but they usually cannot measure the field directly. The world listed as potentially habitable may have a carefully measured meteors from the weakly record field or magnitude. No star may matter as much to the planet. Many of the most accessible potentially temporal super-Earths orbit around the worlds. These stars are smaller, cooler, and much dimmer than the Sun. The habitable zones are close to them, allowing planets and temperate conditions to compete in orbit in days or weeks. This creates an observational advantage. Close planet transits often give astronomers repeated chances to measure it. The planet also blocks a larger fraction of small stars light from blocking the sunlight scattering. The gravitational pull on the star is easier to detect. The disadvantage is that red dwarfs can be highly active, especially when young, produce flares and strong ultraviolet and X-ray radiation. Their stellar rings can affect atmospheres and close radiation. The planet may finally receive a comfortable amount of neutral energy while having spent its youth exposed to conditions capable of removing nature and planets. The red dwarf also changes slowly as it settles onto one sequence. During its long early phase, it can be brighter relative to its later output. The planet now sitting in the habitable zone may once have experienced intense heating. Oceans could evaporate, water vapor could rise into the upper atmosphere, and ultraviolet radiation could split molecules. Hydrogen escapes easily, potentially leaving the world dry with rich in oxygen and not producing life. Models of water evolution on late dwarf show a wide range of outcomes. A rocky super-Earth can retain large water reserves, become an ocean-flooded world, or lose enough water to become dry. Planetary mass helps with retention. The initial water supply, orbital position, atmospheric escape, exchange of water with the planet all matter. Some simulations find that only a limited range of starting ocean waters produces the Earth-like environments of oceans and exposed land. Closer planets are also likely to be entirely locked. Their rotation slows until one rotation takes the same amount of time as one orbit. One side faces the star permanently, while the other remains in darkness. This one seen automatically constrains habitability. The day side might overheat, while the night side will become cold enough for the atmosphere to freeze. Climate models have shown that tidal locking is not necessary to produce those extremes. An atmosphere can move heat from the day side to the night side. Oceans can also transport energy. Clouds may form over a region, facing the stars and reflect part of the incoming radiation. Depending on the atmospheric pressure and water supply, the planet can maintain moderate conditions across a substantial area. Some models produce an eyeball climate, with open water never directly facing the star and ice across much of the remaining surface. Others allow habitable temperatures near the boundary between permanent day and permanent night. Recent climate calculations continue to find multiple possible regimes for synchronously rotating planets, including limited temperate regions at its day-night boundary. Living on such a world would be unequal on Earth. The sun would not rise or set. Weather might move consistently between the hot and cold hemispheres. One side could have a permanent bright sky, another permanent darkness, and a broad ring of twilight between them. None of that prevents microorganisms from existing. It really prevents the planet from being like Earth, something planets show very little concern about doing. Water creates a perfect application. Super-Earth can contain much more of it than our planet. Earth is often called an ocean world because water covers most of its surface. Water represents only a very small fraction of its total mass. Increase that fraction substantially, and a planet can develop an ocean hundreds or thousands of kilometers deep. At the bottom of such an ocean, pressure becomes enormous. Water no longer behaves only as familiar liquid or ordinary ice. It forms dense, high-pressure phases of ice, even while the material above is liquid. This layer may separate the ocean from the rocky mantle. On Earth, seawater attracts the crust of the ocean floor. Minerals, wheat, and chemicals molecules move between rock and water. Hydrothermal systems provide chemical energy and are often discussed as possible settings for the origin of life. The high-pressure ice layer can reduce or alter that exchange. Nutrients may become limited. Carbon cycles will function differently. The ocean might remain stable, but stability alone is not enough. Life requires usable energy and chemical materials. The opposite possibility is that high-pressure ice does not completely prevent exchange. Convection, melting, fractures, or upgrade material that transport chemicals through it. The water-rich superworld could contain several distinct internal layers, each capable of moving materials slowly. We do not yet know whether the deep ocean improves the chance of life by providing a large stable habitat or reduces it by cutting the water off from its rocks. It may do both, depending on the depth of the material activity. One of the strongest candidates for detailed study is LHS 194 AD. Journey to red dwarf about 49 light years away, has a radius around 1.7 times Earth's and mass several times Earth's on a roughly 25-day orbit. Its density is lower than expected for a planet with only Earth-like proportions of biological life. This initially allowed two broad explanations. It could be a rocky core surrounded by a light hydrogen-rich atmosphere, making it a small sun-like tube. Alternatively, it could contain a large quantity of water. James Webb Space Telescope observations have not shown the prominent features expected from a hydrogen-dominated atmosphere. Two independent 2024 analyses favored a high molecular weight atmosphere for water-rich interpretation, although the atmospheric signal remained competitive. One team reported that an atmosphere dominated by nitrogen had particular features, and that thick hydrogen-rich models were strongly disfavored. Another concluded that the water world scenario remained the best explanation for its low density, after hydrogen-rich atmospheres were excluded by their models. This does not mean astronomers have discovered the inhabited ocean. It means they have identified the planetary conditions worth investigating. LHS 114 is a large global ocean, its on its surface, a limited region of liquid water, a thick atmosphere, or no substantial atmosphere at all. Additional observations are needed to confirm whether its gases include nitrogen, carbon dioxide, water vapor, or something else. The planet is useful as the possible answers are scientifically important, even if none involves life. Confirming a water-rich super-Earth will reveal how planets collect to maintain volatiles. Detecting a heavy atmosphere on the rocky planet orbiting a red dwarf would show that such atmospheres can survive stellar activity. Finding an air surface will provide a different constructive atmospheric loss. TOI 715 is another example. It lies about 137 light years away, has a radius roughly 1.55 times Earth's, its orbit in 90.3 days around the red dwarf. Its orbit falls within a conservative estimate of the star's habitable zone. Its measured size places it near the region where planets change from predominantly rocky worlds to gas-rich ones, making its composition especially important. We do not yet know whether it has an atmosphere. We do not know whether it has water. According to habitable zone super-Earth describes its size and energy received from its surface. This careful language can feel less exciting than the nonsense of the Earth, but it is more useful. Habitability is not one measurement, it is achievement conditions. Every one must be investigated separately. Can atmospheres be real rather than a false signal? Its size and mass must be measured. Its density must be interpreted. Its star's radiation and age must be understood. Atmosphere must be detected, then its composition examined. Climate models must determine whether the measured gases can support liquid water. Researchers must consider clouds, photochemistry, atmospheric escape, volcanic activity, and the possibility that the planet has no accessible rocky surface. Only then does the search for signs of biology begin. A biosignature is a substance, pattern, or combination that might be produced by life. Oxygen is often mentioned as Photosynthesis contains a large amount of material in its atmosphere. Methane can also be produced biologically. Nitrous oxide, methyl chloride, and other gases have been proposed as constant science. No single gas is a guaranteed discovery of life. Oxygen can be produced without biology. Ultraviolet radiation splits water with carbon dioxide. Methane can be released by geological reactions. A planet may contain both oxygen and methane because its atmosphere is under chemical balance. Even that combination is protected in the context of the star, surface, oceans, and volcanic activity. Life might also be present without creating a detectable atmospheric signal. Earth itself spent much of its history inhabited by microorganisms, while its atmosphere was very difficult to develop. A distant observer with limited instruments has failed to recognize early Earth as living. Clouds and breezes make the task more difficult. The transmission spectrum of high gases below them. The atmospheres of small rocky planets are also thin relative to the size of their host stars, so the signals will be only a few parts per billion. NASA has estimated that even under favorable planetary assumptions, attempting to detect certain proposed biosignatures in LHS 114AB would require tens of work transits, and that's 40 to 200 hours of observing time. Clouds could increase that requirement, while overlapping molecular features make identification harder. The others therefore conducted reconnaissance, rather than delivering a quick census of living worlds. NASA's dedicated rocky road program is now counting about 500 hours to 9 small planets around nearby red dwarfs, including LHS 114AB, to determine how often rocky worlds in the system contain detectable atmospheres. That question must be answered before more ambitious biological interpretations become reliable. If most close and rocky planets around red dwarfs are airless, the search may need to shift toward calmer stars or wider orbits. If many return atmospheres, red dwarf systems become much more promising. Either outcome improves our understanding. Super-Earths may offer more atmospheric signal than true Earth-sized planets, because their atmospheres extend over a larger area, where gravity can help them return gases. That makes them attractive observational targets. The same qualities that make them easier to study can make them less Earth-like. A detectable thick atmosphere may indicate a small reaction rather than a habitable rocky world. Strong gravity may preserve gases that create excessive pressure. The deep ocean may hide the rocky surface. More mass is helpful, bringing it to the point where it changes the planet into something else. Super-Earth support life? The honest answer is yes, under some plausible conditions. A rocky super-Earth with a stable orbit will have liquid water, an atmosphere, geological activity, and sources of chemical energy. Its large size might help it preserve those conditions for a long time. A tidally locked world would still leave enough heat to maintain temperate regions. A water-rich planet could provide an enormous living volume. The answer is not that super-Earths are automatically more habitable than Earth, never too hot. Many probably have thick gaseous envelopes. Some may be entirely covered by deep oceans or ice. Those orbiting active red dwarfs may have lost their atmospheres and water. No super-Earth has been shown to contain life. No atmosphere beyond the solar system is produced to complete biosignature. What astronomers have found is a large set of planets for which the question can be tested. That is already a major challenge. 30 years ago, super-Earths were hypothetical. Astronomers now know that they are common. They measure their masses worldwide and began examining the gases around the field. The next stage requires finding better targets, temperate planets around bright nearby stars, worlds on longer orbits around stars more like the Sun, super-Earths far enough from their stars that their atmospheres have not been very altered by heat. It also requires telescopes able to separate the light of a planet from the glare of its star. Researchers are moving from asking how many such planets exist to asking what they are made of, how they change, and whether any have maintained environments where biology can begin. That change requires several kinds of telescopes, because no single instrument can provide every measurement. One telescope can discover a planet through transit. Another measures the mass through the movement of the host star. A third studies the atmosphere. A fourth searches for additional planets farther out. The final description is assembled from observations made at times, wavelengths, and locations. This is appropriate because a planet is not so strong as a unique form until its radius, mass, surface pressure, ocean depth. The third type of weather, the first class when its discovery, makes its preferred exoplanet catalogue past 6,000 worlds in 2026. The total includes gas giants, Neptune-like planets, super-Earths, and terrestrial worlds discovered in several years. It was a major sampling of a handful early in the 1990s. It remains a very small fraction of the planets in the Milky Way. Most known super-Earths were found through transits. Kepler established their abundance by staring at one region of the sky for years. Thus expanding search was nearly the whole sky, concentrated on bright, relatively nearby stars that are useful for follow-up observations. Transit provides radius in the orbital period. Repeated measurements can show whether the orbit changes or whether other planets disturb the timing. During the transit, a small portion of starlight will pass through the planet's atmosphere, allowing molecules to absorb specific wavelengths. The weakness is geometry. A planet must cross its star from our viewpoint. Most do not. Transit surveys also favour close planets. A planet in a 10-day orbit crosses frequently. A planet resembling Earth produces one transit per year. Confirming a repeating pattern requires several years. Assuming the telescope watches the events continuously, but none of the events occurs during any coordinated interruption. Planets on Neptune-like orbits are far more difficult. Neptune takes 165 years to circle the Sun. An astronomer can observe several complete Neptune-like periods without arranging to continue the project through a rather ambitious succession plan. Radial velocity signatures help fill part of the gap. The planet's gravity moves a star in a shared center of mass. Spectrographs measure the resulting changes in the star's light. This method does not require the planet to transit. It provides a minimum mass or a more precise mass when the orbital information is known. Combined with the transit radius, it yields density. The challenge is that the rocky planet produces a tiny stellar movement. Earth causes the Sun to move at roughly the speed of a slow ball. Stellar surfaces contain spots, convection, magnetic regions, and oscillations that can produce signals larger than a planetary wobble. Astronomers must separate the planet from the behavior of the star. Make observations, monitor stellar activity, compare spectral lines, and use statistical models. A confident mass can require years of work. Ground-based instruments continue improving. The European Southern Observatory's extremely large telescope, the HELIX-T, is designed to measure smaller radial velocity signals and study exoplanet atmospheres with an enormous collective area. ESO expects the telescope to characterize rocky and Neptune-like planets born nearby stars, including southern habitable zones, with high-resolution spectroscopy and direct observations. Direct imaging approaches the problem differently. Instead of measuring what happens to a star, astronomers attempt to collect light from the planet itself. That light will be reflected starlight repeated by the Earth. The difficulty is contrast. An Earth-like planet seen from another system would be about 10 billion times fainter than the Sun. Visible wavelengths are separated by a very small window. The star's glare spreads through the telescope and overwhelms the planet. The chronograph blocks and controls the starlight inside the telescope. A possible alternative for some future missions is a star shell. A separate spacecraft positioned far in front of the telescope to block the star before its light reaches the optics. Directly reflected planetary light is valuable because it can be divided into a spectrum. The spectrum may reveal water vapor, carbon dioxide, oxygen, methane, clouds, surface properties, and temperature. With limited observations can show seasons or rotation. Current direct images mostly show large, young, hot planets on their orbits. Those worlds glow strongly in infrared light and stand far enough from their stars to be separated. Technology must improve considerably before an Earth-like planet beside a sun-like star becomes a routine target. NASA's Meteors roving space telescope will test an important quantum technology. As of August 3rd, 2026, rover is scheduled to launch on August 30th, 2026. Its coronagraph instrument is a technology demonstration intended to suppress starlight and directly publish over planets and circuit stellar disks more effectively than previous space instruments. The chronograph is not expected to photograph any novel. It is designed to prove systems that mutations can develop further. Rover will also expand the planetary sensors through gravitational microlensing. Microlensing occurs when a negative foreground object bends and magnifies light from a more distant star. If the foreground star has a planet, the planet can add brief features to the magnification. The alignment is temporary and does not complete. It can reveal planets that are difficult to detect in transits. Microlensing is particularly useful when it's farther from our stars, including worlds on orbits similar to the outer planets in our system. We can also find free-floating planets that no longer orbit on the star. This is important for the history of super-Earths, as Kepler and TESS can only reveal closer planets. Astronomers still know much less about super-Earths available, Jupiter, or wider distances. Rover is expected to mount grounded missions toward the centre of the Milky Way and detect thousands of planets through microlensing, while its time-domain observations may reveal a much larger population of transiting planets. As it describes the mission's way to extend the census into wide orbits, typical zone distances, ice giant regimes, and other parts of planetary systems fully sampled by telescopes. The broad census may show that super-Earths cover a nearly distance. They instead reveal the close-range compacting systems, but wide-orbit super-Earths follow a different distribution. Microlensing also tests whether many planets are expelled during instabilities that shape many systems. The population of free-floating super-Earths would support the idea that planetary systems frequently build more worlds than the human. Rover will tell us more about their planets and other missions to improve their images and properties. ESA's Plato mission is currently planned for launch in March 2027. It will use 26 cameras to monitor more than 200,000 stars, with a particular focus on terrestrial planets in orbits extending into the multiple zones of sun-like stars. Plato will also measure single oscillations in those stars. Those oscillations allow astronomers to estimate stellar masses, radii, and ages more accurately. Age is one of the sequences in exoplanet science. Kepler provided a snapshot containing planets in known ages. Without precise stellar ages, it can be difficult to determine whether two planet populations formed differently or whether one evolved into the other. The young sun Neptune may lose its atmosphere and become a super-Earth. Close planetary change during the resonance can spread apart over billions of years. Planet's radius changes as its atmosphere cools and contracts. Stellar radiation declines as the star ages. Plato's measurements should allow astronomers to arrange planetary systems along a timeline. They can examine whether the radius band shifts with age, whether the atmospheres disappear, and whether compact systems become unstable early, continually changing for billions of years. The mission will also search young orbits and early transit surveys. A true Earth traveling around the sun-like star requires careful observing of multiple transits. Plato is designed to monitor selected fields long enough to find small planets that units like servers move rapidly across the solar. These worlds are actually particularly important question. As super-Earths hover around sun-like stars at temperate distances, or do they only dominate short orbits and systems around smaller stars? Plato finds many temperate super-Earths beside stars resembling the Sun. The solar system's vicinity becomes even more unusual. If it finds a substantial population of Earth-sized planets without close super-Earth companions, our architecture may belong to a difficult to detect nuclear class. Discovery and measurement will still not be enough. Atmospheres must be examined across a large population. ESA's aerial mission is currently planned for launch in 2031. It is designed to study the atmospheres of around 1,000 exoplanets, ranging from rocky worlds to gas giants. Aerial will measure the effect of the movements of clouds and changes over time, but it will quite an atmospheric survey rather than concentrating on one possible Earth twin. A statistical approach is necessary because individual planets can be misleading. Suppose one close super-Earth has no atmosphere. That may be caused by an unusually active star, a giant collision, and no original gas in there, or extreme heat. It does not tell us what usually happens. Studying hundreds of planets, patterns begin to appear. Atmosphere retention, particle mass, radius, stellar type, orbital distance, and age. Researchers can test whether planets have a certain mass and temperature, whether which worlds form in particular regions, and whether the radius band is produced mainly by stellar radiation or by heat escaping from planetary materials. Aerial will concentrate largely on atmospheres that are observable enough to support the survey, including many warm and hot planets. Those worlds may not be habitable, but are useful laboratories. Complex atmospheric features easier to detect, and studying them helps establish the chemistry and physics needed to interpret cooler planets later. The planet does not indicate any life force when potentially living planets form, but the key worlds reveal how atmospheres are lost. The sub-mention shows how much gas cores can be left. Water-rich planets test migration from cold regions. Systems containing both super-Earths and giant planets reveal whether Jupiter-like areas are common. James Webb continues examining selected targets in greater detail. Webb is powerful enough to search for atmospheres on nearby rocky planets around small stars. The task requires large amounts of observing time. The strength lies in careful investigation of a limited sample rather than consensus. The first useful results are simply determining which planets have air. Mary's world produces strong change in brightness between its top daytime and the night side, and atmosphere produces strong heat. During an eclipse, when the planet passes behind a star, one can measure the loss of infrared light and estimate daytime temperature. Transit observations and search for molecular absorption. Stellar contamination remains a problem. Spots and bright regions on the Earth wall can change the current transit spectrum. The telescope is measuring a small difference between two large quantities of light, and the star is not a perfectly uniform pattern. The LHS 114 OB observations show that comets and notifications. Working to rule out some atmospheric bodies and tentatively favour others. The stellar surface features must be modeled carefully, and additional transits are needed. Ground-based telescopes will work alongside space observatories. ELTs employ this were reflecting up light in high-resolution spectra of nearby planetary systems. Molecules moving with their planet change velocities in orbits allow astronomers to separate their spectral lines from the relative stationary lines of Earth's atmosphere and the host star. The large telescope may also measure planetary rotation, movements, or differences between hemispheres. These are difficult observations, which adds information that cannot be obtained from the recent events alone. The long-term goal is direct imaging of potentially habitable worlds. INSA is developing the concept of habitable worlds observatory. Its main objective is to directly image and characterize at least 25 potentially habitable planets around nearby stars. The observatory would use spectroscopy to search their atmospheres for gases such as oxygen and methane, while also conducting broad astrophysics. The mission remains in development and does not yet have a launch date. Number 25 is important. One planet will be a treated atmosphere, which is years of argument. A sample of several dozen makes it actually possible. Some may have water, but no oxygen. Some may have oxygen produced without life. Some may have thick clouds. Others may resemble dry versions of Earth. Every stars will differ in age and activity. Researchers will look for combinations rather than one magical molecule. Oxygen with methane might be more significant than oxygen alone. Carbon dioxide, water vapor, carbon monoxide, pressure indicators, clouds, and surface temperature all help establish the environmental context. People carefully measure atmospheric environments without reducing distant surface. Scientists will test geological and photochemical alternatives. Independent teams will analyze the data, and the telescopes will repeat the observations. Genuine detection of life will popularize as light becomes stronger over time, not as one dramatic screen suddenly described the world alien. Super Earths will be part of the search, but the next targets will not always carry that label. A planet 1.4 times Earth's radius could be a massive empty world. One at 1.8 times Earth's radius could be a water world or some Neptune. Classification will depend on density and atmosphere, not only on whether radius falls in plateau. The search will also examine systems as complete families. Super Earth's origin may be revealed by its neighbours. The resonant chain suggests migration. A distant giant could indicate a power or source of instability. Similar planet sizes may reflect growth in one shared reservoir. A large gap in the system may mark a collision, ejection, or undetected planet. Precise ages will show when the system becomes stable. Measurements of the star's chemical composition can indicate the available building materials. Observations of debris disks reveal ongoing collisions with leftover reservoirs. Young protoplanetary disks provide the earliest counting timeline. However, the James Webb Space Telescope examines rings, gaps, ice, dust, and organic molecules before planets finish forming. ELT will study the regions of nearby disks where rocky worlds grow. Attracting young disks with mature planetary systems, researchers can test and propose history directly. Do massive inner dust rings become super Earth chains? Do early giant planets create gaps that scarp the disk? Are systems with strong pebble caps less likely to form closer planets? How often do resonant chains survive after gas disappears? At present, many formation models can reproduce one part of the evidence. The model may generate correct pattern sizes but with wrong orbital spacing. Another may create a compact chain of two gas giants. A third may produce the solar system but only under a narrow set of initial conditions. Larger samples will remove some of this freedom. Theory must explain not only our planets, but the statistical patterns across thousands of systems. The worlds our solar system never named are useful precisely because they represent common alternatives. A hot, rocky super-Earth shows what may happen when an inner core grows early and manifests. A subnatural shows what happens when a similar core retains gas. The water-rich super-Earth may reveal formation beyond the snowline and continental. A system with 6 close planets demonstrates that resonant chains can survive. A system with an outer giant and inner super-Earths shows that giant planet plans are not always complete. Everyone provides a comparison with the path taken here. The most revealing discovery may eventually be a true solar system, a sun-like star with no closer planets, several small rocky worlds at moderate distances, Jupiter and a wide circular orbit, ice giants farther out. Finding one will show that our architecture can be repeated. Finding many would suggest current solar time works. They would find